I hope you can all see me and hear me fairly well. Probably we can wait a couple of minutes while all the other people might arrive.
Yeah, we can hear you, but we can see you.
You can't see me. Oh, I turned on my camera.
I can.
You can. Okay.
Oh,
So
so
hopefully
that's my issue.
it's not with my machine. Yeah, I have the camera on. I can just try to turn it on and turn it off and turn it back again. Hopefully
Oh yeah,
it's
now
gonna
it
work.
works. Thank you.
Okay, that's good. Yeah. So I don't know how many people we're expecting. It might be that there's just 6 people on this course or so. I'm not aware of like the number of participants, but we will see. Still, I think it might worth to wait just a couple of minutes, and if like no one else will join, then we can start. Okay, I think we can start, and then others might join later. If you know or are aware of anyone who would like to join but couldn't at this time, then just please uh, let me know. But then I would start just a few administrative things. So in the chat, I sent you links to the materials. So one of the slides I will go through that. That's not the other most important part. I will try to share this. Also, the plan is that after the some theoretical knowledge, we would like to implement some supervised methods, especially like a deep neural network together. That's the aim, to train a deep neural network together. We will do it, or I will do it in Google Colab and in Python. I will try to explain all the steps and all the things there. But if you have any, if you want to do it on your own, that's great. Via the link, you can follow my code as well. I will also share my screen, but from this, the shared code, you can also copy it. You can reach it after the lecture, where you can find it if you think like something is not working on your implementation or things like that. And the third most important thing is that I only have one screen, so I can just see you now. But once I will start to present, I will not be able to see you. So please, at any point, if you have any comments, questions, want to add anything, please just unmute yourself and say it. So I will try to speak continuously. So please just say it as I speak, and I will stop. It's not an interruption. It's not rude at all. I will not. I might miss like you raising your hands or writing in the chat and things like this. So please, if you want to add anything, please do so. It's not rude, not an interruption. I'm glad to any comments, any questions, anything that comes there. And so, if you also have any questions, anything at this point, then just please let me know now. And yeah, and sorry, the last thing what I was thinking of is that the planned schedule of this course is from 4 to 8, with some like 45 minutes lectures and 15 minutes breaks, or uh, like so. I plan to probably have shorter breaks if that's fine with everyone, just around like 5 minute breaks or so at like every hour, and then hopefully with this we can finish a bit earlier, because I know there are people also from Greece. We should finish at like 9 p.m. there, which is fairly late. So with this, hopefully we can finish earlier. But if any point you would also need a break or want to do something, then please just let me know about anything, yeah, whether it's administrative or theoretical. Okay. And so starting, so I'll plan to share my screen, and so hopefully you're able uh, to see it now. Please let me know. And for me, it shows that my screen is shared, so hopefully you can see a small presentation.
Yes, we can see it.
Okay, that's perfect. That's great. Okay, so this course, which should be held on like 3 days, is about supervised and unsupervised learning. And today I plan to speak mostly about the supervised part, but want to also introduce what supervised and unsupervised learning means. So just as a short introduction, with machine learning and deep learning, I think everybody is familiar. There are various breakthroughs in multiple areas, from playing Go to self-driving cars to large language models, and uh, they, they really like change the way how we think about applications, how we approach problems. And the most fundamental elements in this is uh, based on, or like 95% of them are based on supervised learning. So in the large field of machine learning, there are methods which are supervised, there are trainings which are unsupervised tasks, and there are a few examples in between. But first, I just want to go through this one. What this would mean. So the main distinguishing two topics what we have are supervised and unsupervised learning. So in case of supervised learning, typically we have uh, a task, and during the training process, the expected output of the task, what we usually call as the ground truth, is explicitly given. So it means that we know that for this input, for input X, our output should be input Y. This could be a classification task where, for example, we know that for this input, it belongs to the blue circle task. This other input, it belongs to the red cross class, and so on and so on, and we want to separate them. There are multiple, like an infinite number of possible solutions how we can separate them, but during training, the output is explicitly given. It might be a regression task when we say that if this is our input, then our output should be this number, 6.5 or 7.3 or something like that. These are all supervised tasks and supervised training methods. In case of unsupervised learning, the task is given, we know what we have to do, but the expected output is unknown. So for example, we are just given data and the data is not labeled. We don't know what these classes are. And someone, for example, just tells us that, okay, do some sort of grouping or clusterization with this. The typical application of unsupervised training, although it can be, you can imagine it in different applications as well. You can do unsupervised classification, you can do unsupervised dimensional reduction and things like that. But the most typical thing is clusterization, where, for example, we have data and you have to find out the individual groups in the data without someone telling you what these groups are and in which group these input points are belonging. In case of like supervised learning, the typical application is classification, where someone tells you that, okay, this sample belongs to class A and this sample belongs to class B. And as I mentioned, like 95% of the currently used methods are based on supervised training and supervised learning. The reason behind this is that unsupervised learning is typically really ill-defined. So if you think about this, in case of unsupervised learning, this would be a typical unsupervised learning scenario where I give you this set of images and I will give you a task, and your task would be to, okay, group these images somehow. It's up to you. Just create groups from this one. And since we are humans, we typically bring a lot of knowledge with ourselves, which is like a word model or a word knowledge, where most probably all of you would group these images as like, okay, these are the dog images up in the first row, and in the second row, these are all some sort of cat images, like some nice smaller cats and also tigers and things like that. But they are also cats. So dog and cat images. This is one sort of grouping of these samples. But of course, many other clusterization or many other groups could be created. Like I could create 4 groups where I say that these images are of black animals, these are from white animals, mostly brown or brownish elements, and gray ones. That would also exist. Or I could create a group where like this has like grass in the background. That's also a good solution. Or I could put every image into an individual group where I would say that this input pixel, what is the specific color of this pixel here? And then that would also be a good solution. And from a mathematical and theoretical point of view, all these solutions are equally good. So typically, just defining a task, what should be done, and trying to learn this with unsupervised methods. The main problem is why unsupervised learning methods still struggle, although there are great advancements in this field as well. But today I will focus just on supervised learning. But the main problem with unsupervised learning is that typically the data which is interesting for us, which we are dealing with in practical applications, is really high dimensional. And even if you collect many samples, like representing a task, the data is so high dimensional that you can create like arbitrary different groups or arbitrary sets and clusters in it. And in most of the times, they are not practical. They are not about the practical problem. And even in this task, I can say that, okay, the practical task is dog cat classification, for example, but it could be anything else. We don't know what the practical task is. And this is a typical problem there. In case of supervised learning, this task would be something where I say that this is a dog image and this is a cat image. This is a dog image and this is a cat image. And for this, the output should be dog, and for this, the output should be cat. So I explicitly label every sample in my training data. Every input sample is explicitly labeled, and this is how supervised learning is is done. And in, like, as I mentioned, almost everything that works in machine learning is in the field of supervised learning, or somehow is related to supervised learning. So the simplest set of supervised learning would be this: when I explicitly tell that this belongs to class A, this belongs to class B, this is class A, class B, and like that. So the output is explicitly given. Okay, so if this is okay, and okay, just one more time, I want to remind you that please, if you have any questions, comment, then just stop me at any point. Okay, so then I would go to the next part, which covers, hopefully it's clear what are the distinguishing features between supervised and unsupervised learning. And I mentioned that we deal with supervised learning, and today we will implement a deep neural network, which is the most commonly used supervised method. But I also want to show some applications which are still related to the supervised field. Now we will just leave the unsupervised learning to the other part of the course today, but something which might not seem supervised for first, but they are indeed supervised methods, or supervised method with some tricks, and they are really useful in practice. For example, I've mentioned AlphaGo earlier, that we can train an algorithm for playing Go or playing chess or any logical game, basically, or any game even. And here, I don't know whether you would think this is a supervised or an unsupervised learning scenario. You can just guess if you want. If there are no guesses, then I would just say that it's somewhere in between, because if you think about how chess is solved, in a chess game, we will not have explicit outputs for every step. So if our task is to learn what the next step would be, that's impossible to learn in a proper and completely well-defined supervised manner, because the step is not known itself. But if we play a whole game, even though our steps might be stupid, at the end we have supervision, and the supervision is whether these were like steps for a winning game or a losing game. I will try to explain this a bit more later. So as just an interesting part of something where we have supervision, but not directly, and not just every step for the usable task, is typically reinforcement learning. So reinforcement learning involves scenarios where we have an agent who has some sort of actions that will change its environment. So many tasks that you will see in machine learning, and most of the currently working tasks are passive applications, are passive tasks. So we have an input image, which is a constant image. It goes in, and we have some output. We have text goes in, and we have some output and things like that. So here we don't have an environment, and we don't have an agent who will change this environment. In reinforcement learning, whether this is an AI playing chess, or an AI playing Super Mario, or trying to park the car, we have an environment, and it has actions in it. And our task will be to predict what the next good action is. But here, once we make that action, we will not have like feedback about it. So it doesn't seem as like a supervised scenario. And first, it is not really supervised, it's just random. Here the AI tries like random actions until it first finds something which is good. Here good means that how far can the AI with this car get from this parking spot. And if gets punished if it hits something, whether this is another car, whether it's a lamppost, if the AI hits something, that it receives some punishment. And so here you can see that it tries and tries and tries this, and if at certain points it managed to park into this location, even though it hit another car and things like that, it gets a reward. And here this reward and the punishments for hitting someone are the elements of supervision. We have some knowledge coming outside from the system, which will tell us whether what we did is good or what we did is bad. And this is like a strange field of supervision where we don't have supervision for every task. That's why this is really difficult. But in the end of a series of tasks, we have like a supervised feedback. We have reinforcement coming from the system, and we will make our decision based on that one. And here you can see that the method, as it makes multiple attempts, so now we are at like 20,000 attempts, it will become better and better and make like less collisions and manages to park better and better. So you can see that from many different, at the end, many different positions or starting positions, it can learn, okay, how to park there, but there might be some still tricky positions if it like somewhere where it hasn't been before, but still it can learn that. And here, this is also, if we use it in a broader context, this is part of there might be a debate whether this is supervised or unsupervised, but people typically say that reinforcement learning is part of supervised learning because we have supervision, not for every individual step, but for the whole task and the series of tasks. Another example for this, which I wanted to show, is like a simple AI which can learn Super Mario.
Hey everyone, Chris here. Welcome back to another episode of AI Learns. Today I've got something that I'm pretty proud of. An AI that learns to play different levels of Super Mario Bros. This AI didn't just learn to complete the level either. It learned to optimize its path to complete the level as quickly as possible, and it learned some pretty cool techniques along the way. These techniques include a pixel-perfect wall jump and an enemy flagpole glitch. I'll explain this in further detail when we get there. I'm going to pause here for a moment. Before I showcase all of what Mario was able to learn,
So,
Excuse me.
what you see on screen, and more importantly,
Could
what
you
Mario
like
receives.
turn the volume
This is
down
real
on the
Super
video
Mario
when you
Bros.
are
Game running on an
explaining
NES
things
emulator.
because we
Rather
hear
than
the
Oh,
just
you have the
video
video.
louder than you.
Okay.
Yes,
Yeah.
that was
Sorry,
the
just a
issue
quick
for the
comment.
last
I
one, but
couldn't.
it was.
Yeah,
Yeah,
I tried
it's
to
okay.
mute
It's
the.
okay.
Sorry about that. I muted the presentation here. I'm presenting from Google Slides, and I didn't have the audio. I didn't know that the audio is going to.
Oh, I see.
Sorry about
So
that.
we had music and all, and we couldn't hear you.
Oh yeah, so sorry about that. So thanks for letting me know. But yeah, I didn't know this. Sorry about that. It's a strange thing in Teams that it translated the audio. It didn't translate it for me. So okay, then just try to recap it quickly. So here, this is again a scenario where this is supervised training. So this is a simple neural network, a feed-forward neural network, which we plan to implement at the end of like this. These 4 lectures, and based on this, the AI will select what kind of action we want to do, whether it wants to go up, down, left, right, whether it wants to press button A or B. And what it sees is there's no image processing in this one. It just sees the level in like a simplified environment when the whites are empty squares, the brown are squares on which Super Mario can stand, and the red ones are those enemies. If we touch them, then we die. And so as it goes through, you can just see that that's how it goes through a level. And here, the supervision, it comes from not the individual steps. The AI will not know whether a step is good or a step is bad. It will just only learn this from at the end of a level. So how far it can go, how many points will it collect, and when it like reaches the end of the level, it will know that okay, this series of actions were good. So this is reinforcement learning, which is like a special type of supervised learning. Okay, and then the next, which is a typical example of reinforcement learning, but I find it uttermost important, so I have to mention this, that even the first machine learning program, which was created in 1952 by Arthur Samuel, was using self-supervised training. So this was the first program playing checkers. Checkers is a bit simpler game than Go, and here playing it was like not, there were no supervisions for steps. So for a single step, if you make a step, you cannot really judge whether this step is good or not. And so it's not possible to just tell, okay, was this step good or was this step bad? But what basically Arthur Samuel created was a simple game where an algorithm just made steps sort of randomly. And if these steps in the end was like resulting a win, then he said that these are good steps and increase the probability of those steps. If those steps were like ending up in like a losing series of steps, he said that these are bad steps, and he decreased the probability of those steps. And here you can see that there's no supervision for steps, but the algorithm was playing against itself. So he was using the same algorithm with the red pieces and the black pieces. And both steps were made by the algorithm. So apart from draws, every match ended up with one winning part and one losing part. So one player was winning and the other player was naturally losing if it wasn't a draw. And this was self-supervision. So the algorithm played against itself. It evaluated whether its steps were good or bad in one side or the other side. And both moves were changed. The probability of both set of moves on like both sides were changed a little bit. And this way, the algorithm learned to play. And this is also part of supervised training, but self-supervised training. Because I mentioned that like normal supervised training is something where the steps are whether the expected output it's explicitly given. Here, it's not explicitly given what our next step would be or what is a good step or a bad step. But the algorithm on itself, playing a game against itself, managed to create this. And in the end, at the end of the match, it could say that, okay, it seemed that these moves were good. And this way, it could improve. Okay. And this self-supervised training is really commonly used now. For example, in machine learning models, these are used, or sorry, in large language models, these are typically used as pre-training. So if you think about ChatGPT, probably all of you have heard about ChatGPT. GPT stands for Generic Pre-trained Transformer. And here the pre-training means exactly this, that we have a lot of data, and it's difficult to tell to train large language models on complex tasks, such as, if I ask you a question, what the answer should be. And the large amount of training is not on this one. People typically train large language models also in tasks and things like that, but this is done with a method called reinforcement learning with human feedback. Today we will not speak about this, but I just want to speak about the pre-training part, which is also self-supervised training. And in pre-training, what they use is that we get a language and download a lot of text from the internet, and from this, some of the words are just covered. And the machine learning model has to guess from the context, like the words around that, the words before that, or sometimes the words even before and after that cover word, what could be the word which is missing, which was covered. And by this is called self-supervision, because here we will not train the method for solving the generic task that we want, like answering questions or things like that. This is just pre-training, where we train a model to learn a language model, but it will learn it because the explicit output is generated from the text. We don't need like annotated data. We don't need humans to get this one, but it's called self-supervised, because if you just have the text with just a simple mechanical algorithm where you just cover a word and provide the context of the word, you can create the training data without using humans and using extra human knowledge in this one. So that's why this is another special type of supervised training. And this is also self-supervised, just how like the chess algorithms created the data and the quality of the data for themselves. So there a step of moves was a winning move or a losing move. Here, similarly, from the text, we create this one. And that's the same with basically with images. This is something called a master autoencoder, which is still used for transformers for pre-training. So similarly, not for task, for like, telling what's on the image or segmenting objects in the image. But here the task is to explore the existing data. So what they do is that here the input image is in like the third column, and they cover many, many patches there. These are the gray areas. And only from this small amount of patches, the algorithm should extend the data and generate the new outputs, which are like here in the second column, where you can see sometimes it's a bit noisy. Also from the clock, for example, the numbers are missing because those were not really seen, but still can learn it. And here it will not learn any task-specific things from a practical point of view. It will not know whether this is a dog or whether this is a cheetah or what's on the image. Later on, this has to be put into the machine by supervision, where like a human will tell that, okay, this is the output what I want to get for here, that this is a cheetah. That's why this is called pre-training. But in pre-training, the method learns like correlation in the data, how the data looks like, how to interpret the data, just by creating data for itself. And here you don't need to annotate data, you don't need to collect a lot of samples, because annotation means that it's created from the data. We will just use some masks here and mask out some sort of the image. And images are really like, there are a lot of images on the internet. So that's great. And even if you don't know what's on the image, you can use it because you cover parts of it and train the method on that to, okay, from these covered parts, try to like recover uh, the whole original distribution of the data. So that would be another stranger type of self-supervised training. And so if you're familiar with this one, then we can move basically to the next part, which is just a bit of motivation to see that machine learning now, and especially supervised training, become a really common trend. And if you check like the number of publications in AI in the world from 2010 up to 2022, you can see how this number was increasing, and it's still increasing. There was an increase in 2023 as well, and it's difficult to judge at the current point whether this is exponential or or polynomial, or even might be just a linear increase. But still, you can see this, that machine learning, and especially in machine learning, the field of supervised training is extremely important. Also, if we look at this not from a research point of view, but from from the job market, you can still see, although there are some changes, I also want to mention this just for the sake of clarity, that since 2014, even though it's not monotone, but there was a large increase in machine learning jobs until 2021 and 22. Now it seems to be that there might be a smaller decrease, and we don't know what the future will hold. I don't know any reports about in 2024. Some people or experts or in the job market tend to see that on a longer run there might be a continuous increase in a couple of years, or 5 or 10 years, even though there was just a slighter decrease now. But if you look at the longer trend, you can see that machine learning jobs which are out there are still there, and they most of the time require knowledge of some supervised training methods. I didn't mention this, but from supervised training, the most common ones are super vector machines, random forest, and especially, which is the field of modern machine learning, and we will deal with today, as are deep neural networks and the training of deep neural networks. So this is just to put it in a context and to see how important machine learning can be. Okay, why machine learning became so important now, and what are the reasons there? Because I also have to mention that this is a renaissance of neural networks, and renaissance of supervised training of neural networks, because both the methods which are presented in supervised and unsupervised learnings were published earlier. There was like a popular era of artificial intelligence in about like 1980 till maybe 1990s, and maybe even the beginning of the 90s. But after that, like a lot of people said that, okay, this was like a wrong way, and AI is not really working. And now we are in another renaissance where everybody sees that, okay, neural networks are the answer to everything. And theoretically, there aren't so many new things in this one. I just want to mention that, like, there's a famous paper which came out in Nature in 2015. I think the preprint was also there in 2012. But so around 2012 is probably the moment where we count this renaissance of neural network. And one of the authors there, all the authors are great, and like some of them even got a Nobel Prize. But one of them are Yann LeCun, and he also published papers about convolutional neural networks in 1998. Like some of his first papers were presented there. And training deep neural networks with gradient-based methods, which we will learn today, first appeared in an architecture called and with backpropagation algorithm in 1980 by Kunihiko Fukushima. So in this, he created an architecture which was called the neocognitron. And this was about like training multi-layered perceptrons taught with backpropagation. And the scientific community said that, yeah, that's interesting, but it was really not good for anything in practice. So it couldn't be applied, and it couldn't solve like such interesting tasks which we have today, although some of them are still unsolved, but we got closer to solving at least self-driving cars, understanding language, speech and translation, and many things like that. So then if not the theoretical differences, and please don't misunderstand this, there are also theoretical advancements, and there are many important steps, but the fundamentals were put down in the 1980s, and even 1998 convolutional neural networks were published. But so then what was the cause that neural networks are now became that popular? There are 2+1 reasons for this. The first is, and I started to index this with 0, not just because engineers like to index by 0, but because this is the least important. There were some new, or there are still some new machine learning methods and frameworks and new ideas and new tools out there. But this is really the least important. There are two even more important aspects why deep learning started to work and why it is working now on multiple applications and in various applications. But this is undeniable that there are some new ideas. The fundamental ideas are not new, and there are some new tools which really helps us. So, for example, today the plan is that we will use PyTorch for and want to introduce PyTorch for you, which is great in supervised learning because it enables automatic differentiation and so the automatic application of gradient-based optimization. But this is great, but it's not essential to have working deep neural network, but it will definitely help us. The two other reasons which really help this, one is that there are new architectures, and it's just the computational complexity. So if you think about it, when Kunio Fukushima's paper came out in 1980, one of the best computers, which was not a supercomputer that had to be built and was a couple of rooms or maybe even a full building, but something that you could go to the store and you could buy, was the VIC-20, which contained 5 kilobit of RAM and was working with 1 megahertz of CPU frequency. In 2012, when this revolution started, you could go into a store and buy an NVIDIA GeForce GTX 680, which had 4,000 megabytes of RAM, so significantly larger amounts than the 5 kilobyte earlier, and the processing speed was around 1,000 megahertz, so basically 1,000 times faster than in the VIC-20. And this enabled that the complexity of this network has increased. And one reason why deep learning is popular now and why it works, because it reached a potential critical mass where these algorithms became useful. Not because we train them differently or we do different things with them. Or this is partially true, but not mainly because of that, but because of the neocognitron architecture that Fukushima showed was too simple to solve anything. And if you just create an artificial neural network containing 4 or 5 neurons, it's not complex enough to solve something. And if you increase complexity, these methods, and by complexity I mean you can create more complex network containing more neurons, then they become better and better. And so, for example, in GPTs and transformer models, the main architecture was invented in 2016. And since that, GPT-3, 4, 4.0, 01, all the other ones from OpenAI, they have the same architecture. And the main idea has not changed, but the complexity has changed. Like in GPT-4, if I remember correctly, they have 96 layers, and we have millions of neurons or billions of neurons and billions of free parameters, which can be trained. And this is where they work in practical applications. So by complexity, I just mean that we have more number of neurons, more number of processing elements. And with this, we also need more data to train them. And this is the second aspect, that there's a vast amount of data available. Earlier, people, even in the 1980s and even in Jan LeCun's paper, first paper in convolutional neural network in 1998, he tried to investigate things on a couple of images, or 1,000, or 2 dozens of images, or just really just some. And this was not enough to train these methods properly, because they require a huge amount of data. They require like thousands, 100,000s, or millions of samples. But if we can provide them this amount of data, then they have like exceptional performance. And this is why deep learning is really popular now, because at like 2012, we had such an infrastructure thanks to the internet, and this has nothing to do with machine learning, where you could just go up to the internet, and there's, for example, a database called ImageNet, and you could download like hundreds of images of badgers or anything that you want. Basically, it can be found on the web, and it can be found with in a like a fairly large amount. And if you want to work with text, you can similarly go up, and you can find like trillions of words can be downloaded, and algorithms can be trained on that. So this is the two main reasons that we can create computationally more complex networks, and we have significantly more data available. Okay, and so if this is okay and clear, then I just try to go to the next step. And here we would like to introduce you. So this is a really introductory course, that it's not for engineers and mathematicians, but I want to introduce you what is behind training of a neural network and how it can be trained. So how can we consider a neural network or any task in machine learning? So whatever we call in machine learning, and whatever we call like now supervised learning, we will focus on the supervised part. Every problem can be solved, can be like deduced to an input-output problem, where we say that, for example, we have a black box, and this box implements some sort of function. We don't know what's the functionality of this box, but we can generate input and output pairs. For example, we don't know, but some oracle told us that this is the squared function, what it implements. Then if we present an input here, the output would be the squared of that number that we have put here, okay? And so we have a bunch of data points, and the training data would consist of X and Y pairs, where we can train our algorithm here to implement a function which matches this set of X and Y elements. Okay, so this would be a function. Every machine learning algorithm or every neural network can be considered as a function if you step like really far from the details. And a neural network is a special kind of functions which is called like a parametric function. So here what we have is that we have a function, we have input and output elements of X and Y's. So X is our input, Y is our output, and this is given. Somebody will tell us that for this given X, we want to get this expected Y. And so what's inside is that we will have not just our input as a function, but we will also have a parameter as well. From a mathematical point of view, in a parametric function, there's no difference in the input and the parameter. It's only like a difference from an applicational point of view, that the input is given by someone else, and this parameter is given by us. So it's something that we will define. And this is what we can tune. So for example, we can say that this function implements X to the power of P, but we don't know what this proper p-value would be. And training would mean that we will optimize this parameter based on the X and Y values, that someone will show you many X's, each X with its corresponding Y value. And from this XY pairs, we want to identify that, okay, it means what would be the proper P parameter here, which would implement this functionality, which is described by the X and Y values. And if this can be done, if we can optimize these parameters, it means that we train a machine learning algorithm, that we have our inputs and we have our parameters, and the parameters are tuned accordingly to the input-output pairs. And there's a really nice thing in deep neural networks. There's a theorem that if we use a neural network, if it's complex enough, which it means that it contains like a large enough number of neurons. We don't know what this large enough number is, but for a specific problem, it can be empirically tested. Then a neural network can implement an arbitrary function. So even if we don't know what this function is that we're approximating, but it's given by the set of X's and Y's, and we have no idea what this is, but we will have a number of parameters. I will tell you later on what are the parameters in the neural networks. Now, just as a first sketch, you could think about it that the input goes onto these input neurons, and they talk to each other, and how strong this input influences this neuron is basically a parameter. So every connection in this neural network between the individual neurons would be a parameter. And so the statement is that if we have a large number of parameters, which also means a fairly large or large enough number of parameters, then if you get an arbitrary function of x's and y's, and we don't even know what this function is. For example, I can tell you a really abstract function, like for inputs could be images of cars and images of pedestrians. And the output should be that it's 0 if it's a car and y if it's a pedestrian. I don't know what this function is. I cannot give you like an analytical formula for that, or I cannot define you mathematically. But I know that this function exists. How do I know that? Because I can do that. I can implement this function where if you show me an image, I can tell whether there's a car or a pedestrian in it. And so since we know that there is a function that exists, this theorem will state that there exists a neural network which can approximate this function. So which could implement this one in some way. So let me just show you a quick demo here. And yeah, sorry for that. I have to share my browser. So hopefully you can see this small demo. It was created by Andrei Karpati. His name might be familiar for some of you. And so here you can see that here we have our x and y points. So this x and y points, we just show that x axis and y axis, and this is a really simple neural network. We will talk about this later, what a neural network is. And even though I don't know what this function is, I cannot really give an analytical formula for that. And even if I put down new points, I can extend my training set and put down some new points here until the neural network is complex enough, it can approximate this function. And of course, after a while, I can create such a complex input-output set where the neural network will not be able to learn this exactly. It can just, like, as you can see it now, it can just approximate this one. Okay, but if I create like a more complex neural network, maybe I add some more layers. Here I can just do this by simple text. I will add just 2 other layers and increase the number of neurons, and now I change the network. Now training takes a significantly longer time because the network is more complex, and this runs here just in my browser, and maybe I will not wait for the whole task, but this network eventually could learn this really complex task or really complex function, which I just draw here. So this is what I mean by saying that if there is like a large amount of neurons, which are large enough amount of neurons, then we can have a neural network which approximates that function. I hope this is okay, and this is clear. And even if this task is something I mentioned is an abstract task where we have like images of dogs and images of cats, which should be mapped into the numerical representation of zeros and ones, we can have a neural network, and we have a sufficiently large enough set of x's and y's and a sufficiently large and complex neural network, then we can just do this training simply. So I hope this is okay and understandable as a possible motivation. If yes, then we will do just 2 things now in the second part of the course. First, I just want to describe you what artificial neurons are and how an artificial neural network, the simplest type of artificial neural network, a fully connected network, is built. And once we did that, I also want to show you how these networks can be trained and how we can just set their connections exactly the way as we want. And if this is understood, that in the second half of this, in the second 2 parts, I will try to implement this in PyTorch, which is a simple modern machine learning frameworks which is based on Python, and we can do that. So then we can just move on, and I can just show you an artificial neural network. It's really important that many people think that neural networks are imitations of the human brains, because we also have neurons and machine learning is done by neurons and things like that. And this is not true. So at the current state of people year by year understand more and more about the human brain. Biologists try to really deduce functionalities of the human brain, but at this point nobody really knows how the human brain operates. and how like complex and deep thoughts are formed in the human brain. So artificial neural networks are really far from human neurons as far as we know that. The only connection between human neurons and artificial neural networks are just on the level of motivation. So artificial neural networks are motivated by natural neurons and neural networks, but they are not the same. So everybody who says that, like, ChatGPT is some sort of mimicry of the human brain, and because of this it has neurons, it should have a consciousness and other things, that's not true. So it's just a really simple mathematical model. There are many differences between, first let's just see the differences maybe between human neurons and artificial neurons. And no, sorry, first maybe start with the similarities, because I should tell you what an artificial neuron does. And for that, I want to first tell what a human neuron does. So this is a human neuron, and the human neuron contains basically three important parts. There's a nucleus, there's the center of the cell, which it needs to survive. But information processing is done to two things, the dendrites and the axons. So typically every neuron has a fairly high number of dendrites, and dendrites will reach many neurons close by. And these are like where the input comes into the neuron. These are to gather information around, and then this information is summed and processed by this neuron. And typically we have in every neuron something which is called the action potential. This is the kind of behavior that if we will sum up the inputs and the input is not strong enough, then nothing happens. If it reaches a threshold, then there is a signal which will go through the axon, and the axon goes to some other neurons. Typically, in the axon terminals, there are less connections. So a typical neuron brings in information for more neurons than it brings it further. But that's like the behavior is like this, that on the dendrites the information comes in and it will be transferred through the axons to other neurons. So this is just a really simple depiction of a natural neuron. Regarding an artificial neural network, in an artificial neural network, we have our inputs coming from multiple locations. This would be x1, x2, up to xn. So this is our input coming in. The input is already multiple elements. So you could think about it that these are pixels of an images if we do our dog-cat classification. Or these are encoding of characters or words, or in spoken language, like a given value at a given time point. So this goes in. And all these inputs this is one neuron. For a single neuron, all these inputs are coming in and they are summed, but summed with a weighting. So these are the weights that we will learn. These are the parameters, which I just showed earlier of the neural network, that will tell us how important is this input. If this is 0, it means that it's not important at all. If it's a large positive number, it means that it's very important. If it's a large negative number, that it means that it's important in an inhibitory manner. So the less is this value, it's the better. So this, in a weighted manner, these are collected and summed all together here at this element. And after that, we apply some sort of nonlinearity in this one. I will speak a bit more about this nonlinear process. It could be multiple functions, sigmoid, ReLU, and so on and so on. And from this, an activation is created. As this activation is created, this was something that will go to one or a few other neurons in the next layer. So neurons are formed in different layers. Inputs go in. We will weight them. We will sum them. There is a threshold level. This threshold level will tell us, as I mentioned, the action potential here, that if it's under a level, nothing happens. This threshold will be a value which will be added to this sum or subtracted from this sum if this is a negative value. For example, we can say that, like, if it's like -5, then we can say that, okay, if this sum is here, but it's just 5 or less than 5, then it will not reach a given level. And nothing will happen. So for example, I will tell you just the ReLU. The ReLU, the simplest nonlinearity, is just a function where if the values are less than 0, so negative, they will be just threshold it to 0, and if they are positive, they will be kept as they are. So if just the summation is there, it will just tell us if the sum is negative, then nothing happens, then just 0 goes through. If the sum is positive, the positive value will go through. And with this threshold, we can shift this. If this threshold is, for example, -5, then it would mean that if this sum is less than 5, nothing happens. And above 5, the activation, the part which is like larger than 5 will be forwarded. So this is how an artificial neural works. And it really just the resemblance is just two things, that it collects information for a bunch of neighboring elements and transfer it to other elements. Okay. And the human neural network is different in many, many things from an artificial neural network. In one thing, it's that our processing system is generic. We can solve, up to now, we can solve many, many different tasks with the same neural networks. At the current stage of artificial intelligence, this is not true. We use separate neural networks for self-driving cars, for playing Go, and for solving tasks in language learning. Although there are some changes in this one, large language models show that like they are applications which can solve various applications in the field of natural language processing, but not in other fields. So we are still not generic. Also, human neural networks, they operate with a high level of abstract knowledge. So, for example, for us, if we learn something, we can easily build on that on previous knowledge. And if you learn a new symbols, new ABC or numbers in a different language, you can easily learn them from just a couple of examples. Because if you check like a new letter, like a Chinese letter or a Cyrillic letter or Greek letter, if you don't speak Greek or anyhow, then you will not try to learn the symbol, but you learn like specific things, you know, where are corner points, where are edges, intersections, and things like this. And this level of abstract learning doesn't really exist with neural networks. There are methods to improve on this, such as transfer learning and few-shot learning methods and things like that, but still they are really far from human performance. And the third difference would be that neural networks have like really, really low power consumption. Even like GPUs are marvelous in that they do a lot of operations with high parallelism and low energy, but still they require a lot of data, a lot of energy. And training a neural network especially requires like a vast amount of energy, and that's not true for human nervous systems. And also training is different, because in artificial neural networks, training and the usage of the neural network, which we typically refer to as like inference, are separated tasks from each other. In an artificial neural networks, we typically train a neural network and then we use it in practice. And we will not retrain it. And even if we retrain it, it means just that we will store the data or gather new data, and then we will retrain it. With a human neural network, with your brain, wherever you do a task, you have continuous feedback, and you will build your own models about the world, and you will continuously improve, even without supervision, even without someone telling you, you know, what would be the next step or what would be the proper solution for something. You will try to find this out on your own, and the neural network is completely and dynamically changing. People typically say that it's plastic. It's continuously changing. It's not a fixed network. With artificial neural networks, we have the training step, and after that, in the evaluation step or the application step, which we typically call inference, the whole network structure is carved in stone, and we will just use it as it is. So this is just about what an artificial neural network is. And after this point, I plan to like go into more like a mathematical description of an artificial neural network, especially to a feed-forward neural network. But since like the first part has passed, I just want to ask, come back and ask, do you have any questions, comment, or anything at this point? If not, that's good. But then I would propose to have like a short 5-minute break, for example, like now, and then we can continue in like 5 minutes. I also just grab some water. We'll be back soon, and you can also have a rest. Okay, some people showed a thumbs up, so I just wait because someone's still. Some people are still typing, but. I wait for that, or for at least for me, it was showing that someone was typing, but there's no message. So still, let's have just then a 5-minute quick break, and so at like 5 past 5, we can continue. I'll be back soon as well. Okay, welcome back, everyone. I hope you can still hear me and see the slides as well. So let's just continue. So now we want to describe something like this structure, that we have an input consisting of different elements. So basically a vector of input. Every input should be weighted, and then we want to sum them together. So if we think about this, we will end up with a fully connected neural network. This is the simplest, also in some sorts like earlier commonly used neural networks. There are still better ones, like for a longer time, people were using recurrent neural networks and convolutional neural networks as well. Now almost everyone uses like transformer networks. Those are currently the state of the art, but still all the network training and all the other elements can be learned via fully connected networks. So this is what we will investigate. And typically what we have here is just have an input layer. This is not a neural layer. These are not neurons, or if you want to consider them, these are just virtual neurons. This is our input. So just think about it, that now our input can be converted somehow into 3 different numbers. So these are just 3 numbers here. And we will also have an output layer. And this is the functionality. It could be a single neuron here, just one number, whether like it's 0 and 1 if it's classification, or 3 neurons, for example, where we have 3 possible output cases or output classes. Sometimes people use 3 neurons, and this would be represent class 1, class 2, and class 3. And inside them, we can put a bunch of hidden layers. Here it's one hidden layer, but we could do more and more and more. But if we want to see how it basically just works, then we will have a single input, and X, like this element, is represented by, the input is represented by this X. So this would mean that if this is like 3 numbers, X is a vector containing these 3 numbers, just one after each other. And so what happens first is that every blue neuron here will collect the input from every other neurons in the previous layer. Or if you want to see this differently, then every input element here will communicate to every neurons here, but with a different weight. So if we want to show this, like this is how it would look like. So if you, and I will try to draw now a little bit. If we want to just consider this element, and let's say this is xi, okay, this is our first input. Then this would be agi, let's call this neuron agi, which is our hidden neuron, the first hidden neuron in this layer, and that this would be x2, and this would be x3, okay. And so if we would like to see the operation of agi, then let me just, sorry, my drawing will be really ugly, but this is xi, x1, sorry, x2, x3, and each of them will communicate to agi, okay, so like in this direction. And the communication strengths are something that we will train. So this would be weight 1, this would be weight 2. If we just select a simple neuron here, this would be weight 3, okay. So if I want to write this in like a mathematical formulation, then what will be the input of agi? It will be 3 elements. It would be x1 multiplied by, oh, sorry, it's difficult to write me with a touchpad, or with w1. And I will have x2, w2, and I will have x3, w3, and I sum them, right? If I sum all these 3 elements, this would be the input on H1, okay? So now I could just, on these 3 inputs, I could just write this here, that basically what happens is, if I consider this as vector, that this is vector x, x1, x2, x3, then if this is a vector, I can multiply this with another vector, which is called a dot product between 2 vectors, which is an element-wise multiplication. So for the 3 inputs, I have my 3 weights, and if I multiply them together, then I will get the sum of all activations on H1, right? This is what I would get. Okay. What about H2? If I investigate the second neuron in this layer, then the inputs are exactly the same, right? But for them, I need some new weights. So let me just put some other weights here. This is going to the first neuron. So this is W1, W2, and W3, and I can also multiply it with W1, 2, which would be another weight, which connects X1 to H2. It would be this line here, the strength of this line. And I would have W22 and W32 as well, right? And this would determine the sum on H2 as well, okay? So if I have H3, H4, H5, here I would have like 3 other rows. And if you check this, then it's really nice mathematically, because this is nothing else than just a vector matrix multiplication. If I have n number of, let's say, okay, I have I number of neurons here, which is 3 in this case. I have large H number of neurons here, which is 5. Then here I have a vector which contains I elements, and I will multiply this with a matrix containing I rows and H columns, okay? And this will result in a vector containing H elements. Sorry. And this is really great, and it's good luck, because it means that a single layer, how these axes are connected to these H neurons in the hidden layer, is basically a mapping, which is nothing else than just a vector matrix multiplication. And GPUs and current machines are really good in that one, implementing this sort of multiplication. So, and that's a huge luck of machine learning and artificial intelligence that this can be created, okay? And if we use like the next layer on that one, H2, it's, sorry, let me just go back and delete this from here. Can I was hoping, I tried this out, and at that time when I went to the next slide, and it got automatically deleted. Now it remains there. Sorry, maybe I just skip from the slideshow, and then let me share again. Sorry, it's not the most elegant way of doing this, but okay, now it's created. So we were here that now this vector matrix multiplication on A1 created this one, and that's a new representation. That's just another vector. Now, from my vector containing 3 elements, I have 5 other numbers representing something which we can train. We don't exactly, or might not exactly know what that is, but that's just another mapping, which is described here by this blue notation. And that this mapping is like in the same way is mapped to 3 elements. So now this 5 long vector is multiplied by a matrix containing 5 rows and 3 columns, and we will end up with a vector containing 3 elements, okay? And that's the next one. So here, every layer and many consecutive layers could be mapped. So if we want to write this, like the whole part, up to this point I was just speaking about this vector matrix multiplication, a single layer or a single neuron could be like considered this way, that if I have an input vector of x from x1, 2, 3 to n, and I have weight for this, w1, 2, 3, again to n, if I multiply them together, then I get a number. Then I add the threshold to this bias. I didn't speak about this at like the previous slide, but earlier I mentioned this, that there's this threshold with which I shift the whole thing, and it goes through a nonlinear activation, right? This was the ReLU function where we, for example, said that, okay, if the values are larger than a given element, then the value is kept as it is. If it's smaller, then it's set to 0. Okay. So this was a single neuron. If I have multiple neurons and think about them as a vector, then I can just say that, okay, my input is still a vector. I multiply it with a matrix. A matrix is just a set of vectors, like every column there will be a vector. So the input vector is turned into a vector representation. The bias, again, is a vector because every element will be just just shifted by this B. It goes through a nonlinearity. And so this is the mathematical description of not just a single neuron, but a single layer. And if I have multiple layers, then I can just have a notation that AL of X, like a neural network in layer L, will be that I get the representation in the first layer, where I use this mapping L minus 1 on X, whatever it was. In the first layer, there's no mapping. I multiply it with the according weights, and this means that every element here summarizes the information in this one in a special way, which is learned by us. We will shift it, and it goes through a nonlinearity and get a new vector representation for that one. So that would be just, in a nutshell, a quick mathematical description of a fully connected neural network. And even if we have like multiple elements on that one, just multiple layers, this would be my input layer, for example. Then it goes to the first layer. This is this vector representation multiplied by a matrix. Then add the bias to them and goes to a nonlinearity, and then we will get this vector. Okay, this is the mathematical representation. The geometrical representation is that every element here, like or in this input, we will sum all the information coming from here with different parameters, which will tell us, like, for this element, which input is how important. Like the level of importance is listed there. We will add the bias, and it goes through a nonlinearity. And then we get this layer, and we go to the next one. Same mapping happens, but with different parameters. Again, a similar mapping happens with different parameters. So we will change the representation, which is learned layer by layer, and more layers we have, more complex functions we can implement by a neural network. And in the end, we have some sort of output at the end of the network. So this is how it can be trained, so how it's created, and this is a typical network architecture. And so just the summation is a vector matrix multiplication, which is an elementary operation in computer science. So that's why it's really good and easy to process such networks. Advantages of this network is that this is a network where all connections are possible. So by this is sort of a generic architecture. So it could happen that some of the connections are not needed. Like this input element is not important for us. It's good that this network allows anything to be learned by this network. It can learn that the weights here should be zeros. It could happen. So that's a good point. The disadvantages of such an architecture is that we have a fairly high number of connections. Just think about it. If we have like 100 neurons in this layer and 100 neurons in these layers, then we have all kinds of possible connections between them, which means that every neuron is connected to every other neuron in the next layer, which means that altogether we will have 10,000 neurons, 10,000 connections between them. So 10,000 parameters just in a single layer. Another problem is that they are sensitive to shift. So just imagine that we have our input vector here from x1, 2, 3 to n, and then this is shifted. It might be shifted fairly commonly in practical applications. Think about it that you have an image. It's an image of a cat or a dog. This is my typical example for today that we want to classify them. If you shift this image as 1 pixel, the content shouldn't change in the terms of an application, from an applicational point of view, that it's still a dog or it's still a cat. But the representation has changed. Like this neuron sum this pixel with a given weights. Now this input will be weighted the same with the same value. So that's not a good thing. That was fixed with convolutional neural networks. I will not speak about those today, but if you're interested, then you can look them up or hear about them later on. And another thing is that wiring is fixed, and people typically say that the representation here is not context aware. Like in the first layer, if I put a number here, then only this number is interpreted, and it doesn't matter what are the elements around that. Of course, this will sum them, so this element will consider it, but just in the simple weight, just the element point-wise is interpreted. And in many times, this interpretation depends on the context of the values, and this is completely missing from the fully connected architecture. It was fixed with transformers. In transformers network, this is done, but we will not speak about this. This is still just an introductory course and with introductory steps. But so this is a fully connected network architecture. Okay, so for the next step, I want to tell, I didn't speak much about this, what kind of activation functions do we typically use? The most common activation functions are the ReLU activations, which is, you can see even the definition here. If we have an input Z, then the ReLU does is it's the maximal element between 0 and Z. So this means that if Z is larger than 0, then the output is Z. If Z is less than 0, then the output is 0. Okay, so it just said that if our input doesn't reach a threshold, then we say nothing. Otherwise, we say what the input was. ReLU has some variants: Swish, Mish, Celu, Leaky ReLU, and there are many different types with certain specialties. We don't have time to cover them now, but if you're interested, you can look into them. Earlier, other nonlinearities was also used. Now they are less popular. It's a sort of an empirical thing, but if you train a neural network with ReLU activation, usually you get the highest possible accuracy. If you train them with sigmoid or tangent hyperbolic, those are different. Like sigmoid activations, we just match all the activations between minus infinity and all the inputs from minus infinity to infinity between 0 and 1. The tangent hyperbolicus does the same between -1 and +1. So these are similar. Okay. So now what we know is that we have a mathematical description of a neural network layer. A neural network layer basically is that for every neuron, we sum the input of the previous layer with the weights, add the bias of a proper element, and that would be the new representation, and it goes through a nonlinearity, and we get a new vector. And we will just put these layers one after each other, and with this we can create a deep neural network which can be trained. And I mentioned this, that if we contain like a sufficiently high amount of layers and a sufficiently high amount of neurons, this is a universal function approximator, which means that any function what you can imagine can be approximated by this. So if we have like the number of layers and the number of neurons is high enough, any function you will invent, it can be learned by these artificial structures. Okay, but then the big question still remains that how can we train these algorithms? Because of course, if we create them, then training would mean that we want to optimize the parameters in this one. This is our input from the previous layer. So our parameters, and the nonlinearity is set. That's a given thing. It has no parameters here. So the parameters that we train are the W weights and the bias. So the threshold for the activation and the connection strengths from the earlier input elements. This is what we will train. And you can imagine that if you create this network and just set these values to random values, it will implement a random function. So it will not do what we want to do. And this is what I want to focus now on this part. Why an example task? Or example task would be classification. Okay, classification would mean that we want to have to distinguish between two different classes. One class is the class of green elements, the other is the class of red elements. Okay, and this would mean that we have a separating boundary between numerically. For example, if the green class is represented by 0, an output of 0, and the red is represented by the output of 1, then the classification boundary would be where the network gives back answers of 0.5, where it cannot really decide. But then we will say everything which is larger than 0.5 belongs to the class red, and everything which is smaller than that belongs to class green. And of course, in practice, it doesn't look like this, but it looks something like this. We have multiple elements and more intricate decision boundaries between these two different classes. So if we want to train a network like that, and we speak about supervised training, then I said that the expected output is given. So this can be translated in like that. There is like an expert system, which is typically the human brain or some other algorithm or something where we want to copy the knowledge from this one. So in this example, we will say that we want to classify cute cats and dogs. So we have a really cute cat image, and we have labeled data by this. And by labeled data, I mean that we have a functionality where someone created input-output pairs that for cats or cat images, the output is that this is a cat, and for dog images, the output is that this is a dog. And of course, we cannot have like cat and dog strings coming up, so we will have some numerical representation. And this numerical representation would mean that I will just assume the probability that this belongs to a cat. So it should give us a 0 probability if it's a dog. Then it means that it's an image of a cat, and it should put out a number of 100 or 1 or whatever this number is, a large number. If it's a cat, it means that it has a high probability that this is a cat. So we have this expert system, and what we want to do is we want to copy this system to a neural network. And copying this system would mean that here I have my input, I have like my expert system who tells me that, okay, for this X, this is the expected Y, what you want to get. And I create a neural network. If I create them, I know how to create them. This is basically a matrix vector multiplication. This is another matrix vector multiplication, and so on. I put them in like a consecutive chain. That's great. But if the parameters are set up randomly, then I will get a random answer. Here I will not get the exact answer what I want. And that's why my expected answer is noted by Y. And the actual answer I get from the network is noted by Y prime. So this is what the neural network will give back to me. And here, there is a trick to do the training. And for this, I need something which is called the distance between Y and Y hat, or sometimes we can call it as an error function or loss function in neural network training, where I can say that what's the difference between these two elements. For example, if I show the cat image, then the output should be 1. That's good. And if I will not get 1, but I get like 0.6, then I can tell how far I am for this element. And there are multiple loss functions for this one. And the loss functions here are like some examples for that, but there's like an infinite possible variations. It could be like L1 distance, which is like, for example, an absolute distance between the two. For example, if I expect 1, but I get 0.6, then the difference, absolute distance, is 0.4. But that's the same number of error if I expect 1 and I get 1.4 as well, then the distance is again 0.4. Or I can have an L2 distance, which is a squared distance. But it means that if I will not get the expected output, I get something which is either smaller or larger, then I get something similar. And we also have something which is typically used. This is the cross-entropy loss. It measures the distance between two probability distribution. I will not have time to go into the details there, but in classification tasks, this is the most typically used loss function, where Ti would mean the expected value here, whether this is 0 and 1, and Y hat would be Pi here for all the possible inputs, where I use the logarithm of this one. Okay. And so if this can be done, then there's a really nice thing in this one, that if I know this error function, then everything what happens in a neural network, and also this distance function, is differentiable. A function is differentiable, where it means that I can calculate its derivative, and the derivative of a function would mean that if that function would just stop behaving at one point. So if I have just any function, let's say it's a sinusoidal, and at any point I say that I stop this function, how would this function be substituted by a linear function? So if I just want to write here a times x plus b, for example, then what would be the linear substitution of this function? That's the derivative of a function. And it also tells us a really important thing. It will tell us at every point whether a function is decreasing or increasing. So what we can do is we can differentiate this d point, and by differentiating it, we can tell at one point whether the error function increases or decreases. And this is the gradient of this d point, and we can use this to train our neural network. So how can we train our neural network? I just want to show you this. Let's imagine that we have a neural network with two parameters. The two parameters are theta I and theta j. And these are two parameters that we want to optimize. How can we train them? If we use any input, it would mean that we will evaluate for a given theta I and theta j, and we will get the error from that. That would be c theta. Okay, this is our error, or the distance, how far we are from the expected solution. And this is the error function plotted here, but in practice, we don't see this error function. This error function is not visible for us because we don't see that for every theta I and theta j value. We can only see them in certain values. We can try it out for this exact theta I and theta j value. This is another point when I can try it out, and this would be a third point, for example, where I can try it out. But these are just individual points. We wouldn't see the functions. But knowing that this error function is differentiable, it means that I'm not only seeing this point, but I see the derivative of this error function at this point, which will tell me like which direction will this error function increase, and that's a bad direction, but in this direction it will be better. So I should move into this direction, and there I will get a lower error. If I start from here, I can just go down step by step here on this error function, because if I evaluate this in one point, then it will also tell me in which direction will the points decrease. So this is the main idea of gradient-based optimization. And I don't have time, and also there's no expected knowledge for this short course in terms of derivatives and things like that. But an analogy for this training would be that gradient-based methods are also sometimes called hill climbing methods. So you could just think about it that this is a hill, we are on a hill, and we want to come down from the hill to the lowest possible point. And we don't have a map of the hill. We don't know how the hill looks like, but we're standing at one point. And the only thing that these gradient-based methods will give us is something similar as like if you would just move your feet around a little bit, and you can feel in which direction this error function is increasing, and in which direction this is decreasing. And if you're standing on a hill, just look around, and you know that, okay, I make a step in this direction because that's the direction where the error is decreasing. Once you made your step, you can again look around with your feet. That's the calculation of the derivative, or the calculation of the gradient, with other words, at this point. And it will tell you which direction to go, which is the steepest going down. And you can imagine that from this point, you would just go down to the lowest point of the error function, and you could minimize the error. And this is why, like these hill climbing methods are really commonly used and really practical. There are, of course, certain problems with hill climbing methods. So, for example, if I started from here, I might end up in this region, not in this where the error is significantly lower. For this, you can have multiple initialization and try this out. But for example, if you end up with a saddle point or a local minima, you could stop there. And for this, there are other methods for optimization with momentum and other things, which are solved. I will not have time, and I don't want to speak about them, but just want to mention that local minima is also something which is not fully theoretically solved in this sort of optimizations, but in practice, there are pretty efficient methods for solving this one. And so this would mean that if I have a neural network, sorry, I just want to go back here, and I get an error, and I initialize it with random weights at the beginning. So these random weights are set here. And an input goes through on the network, and I get an output at the end. Then, because I can calculate the derivative of all these operations, I can calculate how to change these parameters to get an output which is a little bit closer to the actual expected output than what I got at this network. So I can improve the performance of the network just a little bit and just gradually. So this is what happens here. And so if I want to show you in practice, sorry, let me just show you a quick video, and let me just mute it, because then I know you get the sound. This is how it looks like. So we started from one point, and this is the error, and we go further and further and further step by step. This is, again, we're doing a lot of computations, and we end up at one point where the error is possibly the lowest, and this is how we can optimize this without seeing this surface, without seeing the colorful surface or seeing anything there. And if any point we started, we can go down to a fairly low point of this error surface just automatically. So this is the main idea behind neural network training. And so this is gradient-based method. There's another element in this one, which is called backpropagation algorithm. Because if I have the error here, I can calculate how to change this parameter. But if I'm going further and further in the structure, then it's difficult how to calculate the error there. There's a mathematical rule for that, which is called the chain rule. And this chain rule is used in the backpropagation algorithm. But I don't want to tell you the mathematical details. Again, here I can just give you an analogy that if you have like a complex system built of like multiple layers, how to propagate the error back. And this is exactly what this algorithm does. And it can be used also in like complex structures. So think about it, for example, you have a hotel. And in a hotel, you have certain inputs, guests are coming in, you have many things in the hotel, rooms, restaurants, entertainment, really anything you can imagine. And your output is the rating of the hotel. You don't see whether like, something is good individually, whether like a restaurant is good or whether like, cleaning is good or like individual stuff. You don't know about them because you're really high level. But since this is a connected structure, if you get like a bad review, what happens is that you can talk to one level below you. If you're the CEO of a big company or like, the director of a hotel, you will just call all the managers in and tell them, like the manager of the restaurant, for example, that there are problems, like, we want to have better reviews, you have to work harder and things like that. And you also call in the room service or the manager of the cleaners and tell the same thing to them, like propagate the error back. For example, you can imagine like the CEO shouting to the managers like one level below them. And each of them will know their employees, and you don't have to know them, and he will know like what is their performance. If he knows that, okay, but I know that like they're really good, give good answers, I cannot really change anything on them, then the error will not be propagated. If it knows that like, yeah, I know that the restaurant is not functioning well and it's not good, then he propagates the error back, and he will know his employees just one level, because it knows, by knowing, I mean, he will know their inputs, that who does a good job and maybe will not propagate the error back. For good employees, he will tell that, okay, there's no problem with you, you shouldn't change. But he will know that if you would change your behavior, your output should change a lot, and it would change the overall output a lot, because many errors coming from that one. And this is like the main idea in back propagation, how from layer by layer, the error can be propagated back to each individual without knowing like what's the effect of this operation, what's like the effect of the first multiplication here for the end result. Okay, and this is the other step. And we put these two things together, back propagation and gradient based optimization, then we can train a neural network, and we can we can train a neural network, and we can end up with a properly trained network output. So if you think about this is how it would look like. We have our expert system, and it tells us that this is a cat. It means that we want to have like 100% cat. Instead of this, we will initialize a random neural network, which will give us a random answer. So it will tell us, yeah, it's 50% likely that that's a cat on the output. Okay. But this 50% means that I not only know how good this answer is, because it's 50% further what I expected, but because of this gradient-based optimization, I know how to change the parameters that for this input, this answer should be slightly better. So I can just change it, and I get something where this is like a 70% cat. And if I evaluate this, I can also automatically calculate how to change the parameters based on these gradients, that it should be even up slightly better, and I get something where it's like 100% cat. So that's good. With like multiple steps, I can reach a state where for this input and this output pair, my neural network exactly mimics the operation of this expert system. It implements this function where I don't know what this function is, but based on the input-output pairs, I could implement this. And of course, after this, I show another example. I will show, for example, a dog, and the expected value would be that this is 0% cat. But I've never seen something like this, but I'm in the neural network. It will output something that this is 100% cat. But it still means that I not only know that how bad this answer is, but I know how to change the parameters slightly to have a better result from the network and decrease it to 50%, and the next iteration to 30, and so on and so on. And then I can end up with 0% done. And of course, the training would mean that if you collect me a large set of input samples, a large set of cats and dogs, and you also label them, so you can tell me what are the expected outputs on them, then I can train a neural network which will mimic this behavior. And if I train this on like 1,000,000 samples, then I can stochastically believe in that my whole system will work well. That from the if it was working properly on 1,000,000 samples, then on the 1,000,001 or 1,000,000 first and second and third next samples, it will also work properly. Okay, but it really depends on the inputs that are collected. So the functionality which I'm copying here is the functionality which is represented by the dog and cat images. And because of this, it's generally true that the knowledge that we have is represented by our data and the data set. And this is really important, that if we gather a bunch of samples here, we can train our classifier with these methods, which will classify the red samples and the green samples, and we get this decision boundary. But you know, if in application these are not our samples, but we get something like this, then we can get horrible results because we don't know, we've never trained our method here and on these samples. So our method will be just as good our data is. And I want to show like some examples which shows that these methods and this deep neural network can generalize really well. Probably the most famous example from this, of course, ChatGPT is probably the most famous now, but like in 2005, the whole thing started with something called the large-scale visual recognition challenge, where 1,000 different classes and later 2,000 classes had to be like classified and identified on images. And here you can see like the network answer, that these are images which the network has never seen before, but in all cases it can identify them. And just to show that it generalizes well, you can see it better some cases of misclassifications. And for example, this is my favorite, where people label this image that this is an image of a cherry. And the network said that, no, I don't think this is a cherry, this is an image of a Dalmatian. And of course, there are also berries and other things. Cherry is not in the top 5 guesses of the network, but it shows that they can generalize well. And this is the reason why neural networks are performing really well, because we can show them a vast amount of data nowadays. And the other reason why they have like really good in practice, because they can learn efficient representations in a well-defined, in ill-defined problems, in problems which are not well-defined. And we have to see that we also learn somehow similarly, and most of our practical problems are mathematically ill-defined. So for example, if you think of any practical problem, like, you know, how does a fractured bone looks like on an X-ray image, or what is a car, then it's really difficult to give a mathematical description for this. If you can give a really good mathematical description, then you can find analytical methods to solve that. But most of the cases, we cannot have that. Even in like really simple things, if I tell you like what a car is, everybody thinks that, yeah, it's a well-defined thing. What is a car? But if we extend this, we might have like a really abstract representation of the car in our head, that, okay, this is a car, that's good. But if you try to extend this set, think about whether an SUV is a car. For most people, probably yes. But what about a minivan? If a minivan is a car, is really a van a car? But if a van a car, then maybe what you think about a truck? What about a bus? What about a trolley bus? If a trolley bus is also a car, then is really like a normal tram a car, or then even a train a car, and like that. And you will see that this is not clear. The set of cars might be different for every individual. And we will not learn the definition of car, even when we are young, from like a formal description, that a car is something which has like 4 wheels, because a car might not have 4 wheels, it might have less or more. And there are many differences. We learn this by examples, that people will show us that, look, that's a car, and that's not a car, and that's a car. And this is how we can learn these methods. And in these problems, where we find out that like everybody knows what we speak about when we say what a car is, but it's not a black and white territory, and it's difficult to make like clear distinctions at certain points. What would you call a car and what would you not call a car? Then this method performs extremely well. Okay, so just in the last few minutes in this, I want to speak about also some limitations and typical problems with AI and supervised learning. And the main limitation is that knowledge comes from more data. But I want to show you if like in practice you want to ever apply deep neural networks or any machine learning, how can you cause problems with that, or what are the things that they are not capable of? And after that, we will go to the coding part and try to implement a few things. So the first current limitation is that the current AI is something which is a narrow AI. We don't have like generic artificial intelligence yet. We don't know when we will have or whether we will have or not. But everything that what we have now works on like just a specific domain. Although I have to like say this, that this is like clearly increased with the introduction of LLMs and large language models. Before that, it was even worse, that you needed special neural networks for, I don't know, a given translation from one language to another one, or any like language processing tasks. An LLM can solve most of these tasks, but they cannot really see, or they cannot like behave or control robots. We still, in multiple fields, we use different neural networks, and they have to train separately. And this means that they work also in just a narrow domain. They work in the domain where they were trained. So if you show them samples similar to what they have seen earlier, they can give you like reliable and good answers. But if you show something which is really specific, then the answer can surprise you. And so, for example, you can see like almost nowadays every day you can see some like advertisements like that the ear translator has arrived, that you just buy a device, it sends what you hear to the cloud, it will translate it and give you back the translation. And although there's like a tremendous amount of improvement in the field of machine learning based translation, this is true for like generic conversation. Even like Google has a fairly good machine translation capability. And if you go into the specific domain, this is an example for like 1.5 years ago, when you try to like translate from German to English, like this sentence, which is like the Volkswirtschaftslehre of Nationalökonomie. And so there are a lot of specialized fields of economy in this one, like national economy, political economy, socioeconomy, so on. Google translated this to this sentence, which was the economics of economics, including economics is part of economics. And even the number of economics is not the same as like it was in German. But you can see that it didn't get a, whatever this means with a machine, that it didn't get a feel of what these different types of economies mean. Because this was such a special a sentence from a special field which it has never seen before, and therefore was unable to translate that. That's what I mean, that we typically have a narrow AI, and AI works in like a well-defined domain where we gather training data. But then if you can get a lot of data which represent your problem really well, these methods are in most cases the state of the art and have the best performance what you can do. Okay, another problem is somewhere where like ambiguous outputs are possible. So it's really a typical problem if for an input, multiple possible outputs can be good. For example, image captioning is a typical task where you present an image to a neural network, and the neural network should describe what's on the image. So it's like from image to text. A network should like describe, okay, what's that? And even if you give this out to humans, because you could think, okay, that's something I can train this on, like a set of X and Y's, a set of images with a set of labels. But this is not a well-defined task. If you give this to humans, this is what you will see, that for this image, various people will give back various outputs. And all these outputs are good, but some of them are focusing in the background, some of them on the person, some of them on the snow, and so on. So you cannot really tell how good an answer is, because it's not that an X and Y pair, it's not supervised learning in that sense that for this input, I have an expected ground truth because I don't have one. I have multiple variants, and these ambiguous outputs are handled like really, really badly in case of supervised learning. Okay, so this is one problem. Another problem, which is a typical practical problem. Theoretically, that's just the same, that knowledge is represented by the data. But this is where people who try to do machine learning in practice usually miss something, and this is how you can just get really bad results, is to think whether your data is generic or not, and to think whether your data represents your problem well. And this is something which is not always straightforward and not always just really easy to decide. I want to show you by a famous story, which was like one of the first data science projects ever, and it belongs to Abraham Wald, who was working in the United Kingdom at like the time of the Second World War, and he emigrated from Hungary. And there, the question was, where should they just use extra plating or aircrafts? So the Royal Air Force asked some scientists to identify which are the weak points of aircrafts. And they said, okay, let's do this in like a data focused manner, which was really a great and new thing that time. And this is the data that they collected, plotted on that on the aircrafts, this is what they collected. Where do aircrafts get hit? And scientists on this, they said, and they were really smart people, that, okay, look at it. You can see that they are hit like in the middle of the plane, at the end of the wings. So this is where like some extra plated should be used. But this was false. Abraham was the first who said that the problem with this data is that we only have data from those planes which are hit and manage to return to the base. Especially the data is important which is missing and what we don't have, because those planes which were hit like in the middle of the wings, the middle of the main body, or at the engine, they crashed and they couldn't return. So these are the important parts where the extra plating should be used, and this will help the planes to survive. And this is exactly what they did, and more planes were like surviving the fight. So this was a successful project, but it just showed that the data that was available had no knowledge in that. So in supervised learning, you cannot just use the data directly as it is, especially the data that was missing one important. Of course, this is a really simple case for that one, but really represents that the missing data was important. And if your data doesn't cover like the good practical use cases, then nothing that people could do there. Okay. Another typical mistake is that correlation and causation in a data is two different things, and all these machine learning methods, they measure correlation. So in two data points, there is correlation if they change simultaneously, and many people confuse this, that it means that they are directly connected. So just as a counterexample for this, correlation doesn't really mean that there is causation between them. If there's causation and one data point is explained by the other one, then there is correlation in all cases. And of course, if you look at natural data, the most cases where you have correlation, it is because some sort of causation, but not necessarily. There is a really good webpage which belongs to a data scientist called Tyler Wigan. Also, this plot is from his page. You can check it. He collected many spurious correlations, which seems that the two data points are connected somehow. But we don't expect that there's causation between the two of them, only correlation. So this, for example, this is the connection between worldwide non-commercial space launches and the number of sociology doctorates awarded in the US. Most probably there are no connection between them. So this is a problem, that just the thing that two variables are correlated. If you train your network on that, it will learn that, okay, if I see X, then I know what the output of Y is, and it's not necessary. A typical problem which is in this correlation and causation domain is something called confounding variables. And I want to show you through a nice and simple example, which is like in Europe, it's a common knowledge and part of our culture that storks are the animals, the birds that will bring babies, right? So we know this one. And if you want to check this data and check the number of storks that live in each country, and you check the birth rate in thousands per year in every country, and you plot them, you see a really nice correlation between them. So it seems, of course, now you know that correlation might not mean causation, but if we forget about this, it seems that this explains it, that really storks have to do something with babies because the data points are correlated. But if you think about this, here the correlation happens because of something called confounding variables. There's no connection between storks and birth rate. This is just a myth. Probably, I hope no one is surprised by this. But the reason is that how we collected the data, and this is a typical mistake, is explained by one common variable. This is called the confounding variable. And this would be the land area of a country. Like at each row which I collected, the larger a country is in Europe, of course, it's true that in North there are more, less storks, and in the southern area there are a bit more. So there's some noise. But the larger a country is, more storks are living there. And the larger a country is, there are more people living there. So there are more birds per country. So here the confounding variable would mean that between these two variables, like the number of storks and the birth rate, there are no connections. There's definitely no causation, and there's also no correlation. But the correlation is caused by the thing how I collected the data, because I collected it by country, and there's a third variable which explains both of them. Okay, and if you train something on this, a machine learning method would tell you that, yeah, definitely there's correlation between them, and most probably there's also causation between them. Okay, and another thing which is like also important, that even though there's causation in the data, you cannot tell the direction of the causation. So for example, if you have data of illnesses and certain properties of humans, like for example, weight, just from the data, if there are like no temporal aspects and other things, it's impossible to tell. Even if you see correlation between a certain illness and weight, you cannot tell whether weight is a causing factor in the illness or whether weight is a symptom of the illness. So which one is caused by which? If you don't have temporal data and other aspects, just looking at the data, it's impossible to tell this one. And so for this, I want to just demonstrate it with an example, and hopefully you will remember this. This is one of my favorite graphs. These are the number of UFO sightings from 1972 till 2014. After 2014, everybody has like good quality cameras and cell phones, and it slightly decreased, so it's not that interesting. But here you can see that at like this point, in like 1994, 1993, something happens. Like the number of UFO sightings has increased significantly. I don't know whether anyone has a guess like what happened there, but I also don't know like how many, what is like the average age of the participants. But for those who were like watching TV in 1993, then you could know that the first episode of the X-Files came out in 1993. And so here, definitely, there's some causation between these two elements. But just looking at the data, there are two possible cases. And so this is what I meant. That's just a joke, but just a representation that you will not be able to tell here. There are two possible cases. One is, even if there's causation, let's imagine that there's causation. One thing is that people were watching X-Files, and because of this, they were hallucinating more UFOs and seeing more UFOs. The other hypothesis, which is I think is even more funnier than that, is that we were airing like through space X-Files, and the UFOs were seeing this, and they were just migrating to Earth and coming here to visit how nice place it is, and it's already full of UFOs and aliens. Just how it happened with Game of Thrones, that everybody were going to Iceland and Croatia. And this is also just looking at the data without having any word model and any extra knowledge behind that, just as likely to explain this change in data. And we will never know from the data which direction of the causation is true, whether more UFOs came here because of this, because the X-Files, or whether more people hallucinated the X-Files. And that's what I mean, like, you know, if you have weight and illness, you will never know whether something is a symptom or a result of an effect or a cause of an effect. It's impossible to know that one. Okay, so this was the first sorry, the second part, and altogether the first part. So this would be the lecture. And in the second part, the aim would be that we will implement and we will get familiar with PyTorch and gradient-based optimization. And we will use Google Colab for this one. Here, you can use anything you want. It's also okay if you just follow the code. If you want to implement on your own, you can use anything. Torch is available in Python, also some other languages in Lua and things like that, but I would recommend Python if you want to do that. The easiest way to do that is to open Google Colab. If you have a Google account, then you can just open this notebook, create a copy of that. I will show you just after the break, and there we can implement our code together. So this would have been like the first part. If you have any questions or comment or anything, then just please let me know. And if not, then let's have just another 5-minute break here, and we will continue after that with the coding part and the implementation. Okay, so if there's like no objections, then I'll just have a 5-minute break, and after that I'll be back and we can continue. If you have any questions during that, just please tell something. Hopefully I will hear, or type it in the chat, or you can just send me a direct message as well if there's something you don't want to ask in front of the others. So hi, welcome back everyone. Hopefully you can see my screen. I wanted to just share the screen, and for some reason my browser just collapsed, but I managed to restart it. So now I share it. Hopefully you can see the collab notebook now, and it's shared, and hopefully you can still hear me and see me. If not, then please just let me know somehow in the chat, or somehow we'll try to chat, but I assume that everything is okay since it was okay up to this point. So we were working Google Colab. I don't know how familiar you are with Google Colab. It's a tool provided by Google where we can execute our code on their machines, which is great. And we can also use Python, IPython notebooks in them. So in Python notebooks, we can just code simply with smaller chunks, and then we can execute all these things. And the aim today would be to show you the basic building blocks of Torch. PyTorch, and Torch is a machine learning library which allows this simple and automatic neural network training, which is called like automatic differentiation. Because I don't know how very familiar you are. I mentioned that like this differentiation and derivation is a mathematical operation which is really good. Engineering students and physicists, mathematicians, typically they hate differentiation. So I mean, it's a really cool operation, but it's not that simple to calculate it by hand. And Torch luckily does all these things for us. And I just want to show you how to use this, because with that you can have a really strong tool in your hand. So hopefully if you open this notebook, you can see my code and you will be able to see it live as I'm writing. So even if not just on the shared screen, but if you open the link which I shared there, or if you even want, I can just, for the sake of completeness, reshare it. This is the notebook I will be learning on. You can also follow it there. And you can also, if you go here to file, sorry, mine is in Hungarian, but it should be in the same order. And you can write to a new notebook in Drive, which would be the third one, or you create something which would be the make a copy on Drive from this one, either of them. Then you will get a new notebook on which like you could work. You could write your own code independently from mine and execute it. And by this, you can also try out the things that we are implementing. And you can do it simultaneously while I'm doing this if you have some experience in Python or so. But after that, via this link, you should have exactly the same code what I have. And you can do this also later on. So you can just try to, if it takes a longer time, you can, there are a lot of tools available for Python in the web. You can just search for that, try to do it on your own, come back and check what I did, and to see so what's happening there, and hopefully it will work out. So once this is done, then let's start. So with this, I will just do something which is called import Torch. So I mentioned that this Torch is a modern machine learning library, which can be used and it's really useful. I want to convince you about this now. And import means that we will just use this. So if you write this into any cell, you can create new cells if you come here and add whether you want to add some plain text or code. So today we will write code, and every cell you can execute a cell by either clicking this button or just clicking Shift Enter. With Enter you create a new line, and with Shift Enter you just execute that code. So once we started this, it will connect to the kernel. The code will be executed at Google, and we got back the results. For this, there will be no results. It will be just that, okay, Torch was imported, and we can, once it's done, then we can go to the next cell. Okay, there's this green tick that it was executed without any problems, and now we can write our code further and work with that. Okay, so first, I will just want to do something, use Torch to add two numbers together. Okay, so what I just want to do here is something, add 2 plus 3 together. And of course, if you're familiar with Python, it's simple and easy. You can just do something that, okay, print out what is 2 plus 3. This is the simple Python thing. I will do the same thing in Torch. And for the first few steps, and maybe for the first half hour or something, it might seem like overcomplicated, but hope in the end it will become clear, and you will see how strong tool you will have in your hand that you can do like this automatic differentiation and gradient-based optimization for anything. Okay, so in Torch, the basic building blocks that we will have are called tensors. So I can create a Torch tensor. A tensor is something which is like, if I have a number is just a number, right? If I have a bunch of numbers one after another, as like in a series, this is what I told you, that this is a vector. This could be an input for like our neural network, this vector. If I extend this to 2 dimensions, when I put multiple vectors one after another, and just one more, and like that, so on, then this will be a matrix. People are more familiar with matrices because of the movie probably, but this is a matrix. And I could put multiple matrices on each other, and so on and so on. And these are all called tensors. So a tensor is a generic thing of vectors, matrices, and things like that. And so if I create a tensor, then I will say I will create a tensor and we call it 2. Okay. With this, I created a new number. It's 2. And I can do something that I create another number, which will be 3. Torch tensor 2, torch tensor 3. That's good. Now I created 2 numbers. I want to add them together. I create a new variable, call it result. And I will say that torch, add these 2 together. And this add has 2 parameters. I will add num1 and num2 together. Okay. And now we'll print out the results. Let's see. First, I have 5, okay, and from my torch operations, I have another result, which is tensor 5, okay, that's a 5, so the calculation was done correctly. It's exactly the answer what I wanted to have, and it's a tensor. The good thing that it's a tensor is that, as you've seen, like neural networks are just vector matrix operations. Here, it doesn't matter whether this is a number or a vector or anything, something more complex, like a 3-dimensional matrix or 4-dimensional, I can do the same operations. So what is really cool, if I want to add now 2 vectors, I cannot really add 2 vectors like natively in Python. I can just know that, okay, vector addition works element-wise, so this would be 5 and this would be 10, but I just cannot write that, okay? I can do it by substituting vectors with some built-in types, with lists or some other things, or using some library such as Torch or NumPy, which can handle this. But here, I can just, for Torch, it doesn't matter whether I use a number, a vector, or a matrix. That's why I have tensors. So now I added 2 vectors together. Okay, so this is still working. Okay, and sorry, what was true for the first part at the lecture and for the slides is definitely true for the second one. Please, at any point, just if you have any comments, have anything, please shout it in. Just let me know that, sorry, there's a question in the chat or someone is raising the head or something, and I don't really see you, so please let me know if you have any comments, any questions, or anything is not clear, or anything is like too fast, or maybe, I don't know, you will let me know if it's too slow, but then the course is for many people without deep knowledge in mathematics or programming. So, okay, but let's hoping that this is okay. We can go further, and the next thing that we can have, so let me just, okay, I show this for vectors. I keep this here that we can add just simple numbers. Okay, that's some comments. Adding numbers, adding vectors. Okay, and so the next thing what I can do is I will copy this part and I can add some special property to a tensor where I can say is that this is something which it has a field called requires grad, which tells us that this requires gradient, and in default this is set to false, that like tensors don't require gradient, but I can set this that this is something which requires gradient. And if I add this there, then the result will be, sorry, yeah, I made a mistake. This has to be floating points to have gradients. I explain this in a moment. But if I do this, that this is 2.0 and 3.0 and requires gradient, then I did the calculation. It's exactly the same. This is 5.0. 0 is not written because that's not needed. So the value is 5. And I have something here which is a gradient function on these operations. And if I use such tensors in any calculation with torch, it would mean that their gradient is automatically calculated. So I don't have to do differentiation and gradient-based calculation by hand, which is a tricky thing. It's not a simple thing, but it's really important for optimization and from the modern machine learning. But this library will do for us just automatically. Okay. Just a side note, why it was not working with these two, because this is an integer. And integers cannot have gradients, because an integer is not something where I can have a minor change. The reason of a gradient would be, and that's also a definition, that if I slightly change this, how would the output values change? That's what I use for optimization. If this is 2 and this is an integer number, then I cannot slightly change it, because it should be either 2 or 1 or 3. Like, because of this, every tensor that requires gradient should be a floating point number, because if this is 2.0, then this could be in the next step 2.001. I can just increase this slightly or decrease this slightly, but there are slight changes. So that's why that error was there. Okay. And even if I have this, I can get something which is the gradient of this function. So I can just say that result.grad, and at the current point, this will be empty, but I can ask for this. So it's none. It's written there that the gradient is 0, but it can be calculated. So let's just see how this could be calculated. So what I mentioned is that we need basically 3 things for training a network. So we have some sort of computational model. This is typically of our neural network. This computational model would be that we have our X, it goes through our neural network on Fx, whatever this function is, and we get Y hat, and normally we want to train it on X, Y pairs, right? So this is how training happens. We have a computational model. Okay. If we have a computational model, we also need some sort of error function. We want to calculate the error between y and y prime or y hat or whatever the notation is. And once this error is calculated, I told you that we can propagate this error back. So let's try to do this. And let's try to solve this by a really simple task, okay? Our computational model will not be a complex neural network, but it will be a simple equation. Let's try to solve the following simple equation, which should be 2 plus x equals 7. Okay, I hope everybody can solve this by without even a pen and paper, and it's fairly simple for everyone, but this is what we want to solve now. Okay, 2 plus something equals 7, and we want to get this something, what this something is. Everybody could solve this normally, but let's try to do the modern machine learning way and try to solve this with gradient-based methods, okay? So how can we solve this? We get a value which is randomly initialized. Let's say that we start something, we will try out on X, which we think it's good, but it might not be. Let's initialize this with a simple tensor containing 1, okay? Let's try out what happens if we start with a 1, okay? So, of course, that's not a good solution. We will get 3 instead of 7, but that doesn't matter. That's good. Okay. So, instead of this tensor, I will write something different. From this tensor, I will create a new element in Torch, which is called a parameter. I have a torch.nn. It means in Torch, there's another sub-library or a module called neural networks. That's NN. And I create a parameter from this one. Okay. A parameter is naturally a Torch tensor which contains gradients. And this is something which can be changed by the algorithm. So here I said that this is a number which is initialized as 1, but later on it could be changed. Okay. And I also store an expected output. Expected output is a Torch tensor, and it could be 7. Okay, let's say I have 7 here. Okay, so what is my computational model now? My computational model would be that I will add 2 numbers together. I will add my parameter and 2 together. So here I will create another number. Sorry, let's say this is num2, or even because I wrote this earlier, let's say that num1 would be 2. Okay, and num2 would be the parameter. Okay, so num2 is 2. Oh, sorry, num1 is a number called 2, and num2 is my x, and I have to add these 2 numbers together. Okay, so this is my computational model. This is what I get, and this should be 7. The error what I get here is my difference from 7. Okay, so what I want to get is that I subtract the expected result from this actual result. Okay, basically y prime from y. Okay, and I showed that there are many error functions. Just subtracting them will not be good because I want to minimize the error function. And if this will be smaller and smaller, and if it goes to minus infinity, this error will be larger and larger. The other way around, if I increase this and this goes to infinity, this will be minus a really large number. So that's good for the terms of optimization, but that's not what I want. I want this difference to be 0. So I use the absolute value of these two. Okay, is this okay? And so if I use this calculation now that I have I have a parameter, I have an expected output. Okay, so for every input, I want to find the proper parameter, which gives me 7. I do the calculation, calculate the error, and I can just say something simply, which is error dot backward. Okay, and if I execute this, then the gradient is automatically calculated on this number 2. And if I calculate this one, then I can print this, what is the gradient now, and the gradient will be opposite what you want, because we always do minimization. So if you check the gradient should be a negative number. It means it's -1, because this gradient should be subtracted from this one. It means that this number should be increased to have a slightly better result. Okay, and this whole optimization is done automatically by this method. Please let me know if you have any questions or any comments or anything here. But I just want to quickly recap what we have here. So we have this really simple optimization where we want to find the number, which is, if added to 2, will give us 7. Okay, this is the equation that we want to solve. And we use this gradient-based optimization now to calculate the error, how far we are from that. And just by calculating this simple addition, we get the derivative of this one, we get the gradient, and we see that this gradient shows, the gradient is an opposite because we want to minimize this error, that now we want to subtract -1/4 from this number to have something which would be slightly better. So I could change this to 2, and because this shows that I should increase it. If I increase it, 2, now it should be 3. Let's think what happens if I give a large number, which is 10. Now I get a positive number, which means I should decrease this. So with this simple model, and with just this 4 or 5 lines of code, now I have a tool which will not tell me like how far I am from the good solution, because if I print out the error, it will tell me how far I am from the solution, but it will tell me whether I should increase or decrease this parameter to have a slightly better solution. Okay, and if this can be done, let me just copy this. I can do something even better, because I can have something called the optimizer. Because I could make this change. I could do something that for the number, I would subtract number pod grad or something like this. Okay, and this would be the new number. So I could do something like, I could do something like this to change this parameter. And it works if I have 1 parameter or 2 or something. But in Torch, there is a special tool for changing the parameters. And these are called optimizers. So I will just create now an extra optimizer here. And let's call this opt. And they are in the Torch Optim module. And there are many, many different optimizers. Here you can see them, Adam, Adamax, so on and so on. So I will use something called the Adam optimizer. And it has two parameters. The first parameter is what are those parameters which can be changed. So what are the variables that it should change? Like this is my parameter. Now I will tell them that the only thing that you have to like interact with should be num2. And it also have a parameter which is the learning rate of the algorithm, where we can say like, okay, but how much should you change it? What's the amount of like a small change? I will say that change it with like 0.1 or something, okay? Because if this is a large number, just think about it, it's 10. Then I start with 1. Then it goes up to 11. That's not good. Then it decreases by 10, and then it will just jump around this value, okay? So I will just want to introduce gradual changes. And if I do this computation, then I can do something which is, I can just delete all the gradients in the computational model. Later on, I will tell you why this is important. Please just skip this part now. And after the error is propagated, I can just make something optimizer.step. And this would mean that, okay, once you calculated the gradients, now we know how the parameters should be changed. Change those parameters, okay? So if I just write out number 2 now, after this, we started at 1. All the computation happens. Okay, we calculate the error, everything happens. And the parameter now is not 1, but 1.1 here, okay? So I said that the step or the amount of change which can be done is 0.1. And then I increased this a little bit, and now this parameter is increased. So I just said that, okay, we know the error, act according to the error, and rewrite all the parameters. Okay. So the only thing to have a proper solution now is to use this multiple times, because with these steps, I did my computation, did my error calculation, propagated the error back, and updated the parameters. I get a little bit closer to the good solution. The error was originally 4. Now it's just 3.9, right? So the only thing what I need to do is to iterate this more. If I put this in a cycle, and I will just say that, okay, do this 100 times, then write this, then number 2 will get closer and closer to the good solution, which is 5. Okay, and that's why I needed to optimize 0 gradients here, because once the gradients are propagated back, it's kept. If I will not delete them, then the gradients will be added and added and added for each calculation, and I don't want to do that. For the new parameter, I want to have new gradients. That's why I deleted the gradients here. This optimizer 0 grad, it means that for all the operations which I have here, the gradient will be just set to 0. So again, when I do the calculations, it will be automatically calculated and error will be propagated back. So if I just run this, it always will be written like the parameter. So after a while, I end up at by 5.04 and 5.05 and that like this. You can see that from the beginning. If I just managed to go there, I start with 1.1 and 1.2, 1.3. So my parameter is increasing and my error is decreasing. Okay. The parameter is continuously increasing until I will reach like mostly 5. Here I reach 5. I use floating point variables. So it's really important. This is an engineering tool. This is not a mathematical tool. My solution is not 5 and like that, but it's 5, 0, 0, 0, 0 something. If you calculate, I still have an error here, which is 2 to the power of 2 times 10 to the power of minus 0.6. So there's like a tiny error, but here we have a solution which is sort of good enough. And if you see this, that's why my number will still increase and then it will decrease and so on and so on and so on. But I get, if I run this for a really long time, I get an approximately good solution. The other thing what you see here is that once then my solution starts to oscillate around this value. it comes from the fact that I use something which is called the atom optimizer, which is a pretty good optimizer, but it uses momentum. Because one of the major problems of gradient-based optimizations, I mentioned this, are local minima. A local minima is something where, like, the error is small, and in one direction increases, and in the other direction it also increases, but it's not the best error value what I have. And if I just use the gradient, I would just infinitely step there. And instead of this, we have something which is called optimization with momentum, where my steps as I go down on this error function will be accumulated. And if I saw that in this direction it was fairly good, when it reaches the momentum, it will not come back directly, but the momentum is capped. And if it's just a small thing going up there, then it will go down. And because of this, even if I'm at like the good global minima of the function, with momentum, my optimization will be oscillate around that point. So you can think about it as like, instead of just making one step in the hill climbing method, it looks something as like you would have a ball with some weight, and that would have momentum. Okay, so if you reach the global minima, it will oscillate it, but there is some friction, so it will slow down and will stop at the minima. Okay, is this okay? And is this understandable what I did up to this point? If there are no questions, then I go further. And now I just want to show you that this is an incredibly strong tool, because now we have a generic tool to solve this, that I have a computational model, an optimizer, do my computation, get some error from that, and propagate the error back. Okay, and with this we solved a really simple equation, but not anymore. Let me just copy this and modify this to solve a really complex equation. Okay, I don't know what your equation is. You can invent your own really complex equation. For me, it would be something like this, okay, that it's x multiplied by x to the power of 7, okay, because this is then a 7 orders polynomial, and 7 orders polynomials don't have analytical solutions. And let's say then I add, for example, sinus x and minus 20 times x, and this equals x to the power of 5 plus 3. Okay, this is an ugly equation. We move from a really simple equation to a really ugly one, and we want to solve this now. Okay, how can we solve this equation? With the same tool, and now you will see how simple and elegant this will be. And when I say solution, it's not an analytic solution, it's an approximation of the equation. But from an engineering point of view, this is really good for us. Okay, I have only one parameter. It would be x. I will also decrease the learning rate slightly. Okay, I don't have an expected output, because now my error would be the difference between the two sides of the equation. Okay, so I change the computational model, and here I will have something which is the left side of the equation and the right side of the equation. Okay, and the left side is x plus, there is a built-in operation torch power, which is like x to the power of 7, okay, plus there's a built-in operation of a sinus as well, towards sinus minus 20 times multiplied by x. Okay, so this is the left side. And for the right side, I can just write something which is the power x to the 5th power. Okay, and we add 3 to that. Okay, so this is my two sides. I did my computation. What is my error function? It will be the difference between the left side and the right side. Okay, and I get an error, I propagate this error back, and I print out the error. Okay, so this is what we want. I will not print out the number and x, because I don't know what the solution of this equation might have multiple solutions. What I just want to see is that how close I can get. Okay, I'd run this like maybe 1,000 times, and if I run this, you can see that the error is decreasing. At like one step, I reach the point where the difference between the two sides of the equation is 0.0003. Okay, so it means that I just immediately solving such a complex equation, solving like approximating, but that's good for an engineer. I could just change the computational model, and all the other parts remain the same, and everything is more or less solved, right? So this is a really cool thing now. If you want to like get a numerical solution for any equation, you just change the equation, just change these two parts here, and you get a fairly good solution for that, okay? And of course, there might be problems where you can have equations that these gradient-based methods are numerically unstable and go to infinity and things like that. But in practice, they work really well. They are a really like tools for every usage, and you don't have to calculate the derivatives. It's all done for you by PyTorch, and they are all done for you automatically. So this is a really simple operation to do that. And if you have any questions or comments at this point, then please just let me know. If not, then let me just show you that this is, of course, in the end, we will train a neural network with this one, and we will build our own neural network together. But just want to show how strong this model is, okay? That now instead of solving an equation, because for any equation, you could just rewrite it here, and a torch would just solve it instead of you. We can do something which is called a regression. We can do linear regression, okay? So I have two vectors here. I just copied it here. You can also copy this data from the network. Sorry, from the notebook. I shared the link of the Collab notebook with you in the chat. And sorry, let's just try to plot this first, okay? So I have something called matplotlib. This is a plotting tool. It's not theoretically important, but it would be nice to see the result. So I can just do something where I can say that I plot the x coordinates and the y coordinates. Okay, and let's say I plot them as like red circles. Okay, so this is our data. Okay, and now our tool would be still not a neural network yet, but let me just try to fit the best line on this one. And by best, I mean that I do linear regression. I want to fit a line here where the average distance of the line and a point is minimal. Okay, so I want to put a line here where the line is minimalized. Okay, so how can I do this? What do I have to like modify in this data? Let me just copy my previous computation, because these are the elements that I want to do. And you can see that it will be really easy. So what do I want to do now? I have x points. I want to fit a line there. Equation of a line would be something like w times x plus b, and that should be equal to y, okay? But instead of this, I cannot put just one line on that one. That will be some error. I will get y hat, and I want to minimize this one, okay? So the first thing that I do is I will convert everything into tensors. These are just lists in Python, which are really similar to vectors. They are luckily convertible. So I would say that I create a tensor from the, from the train x part. I will convert this to train y as well, will be converted to a vector. Okay. And this is my computational model. My computational model is a line now. In the line, I have two parameters, the slope and the shift or the offset of the line or the bias of the line. So I will have w, for example, which is a parameter, and I have another parameter which would be the bias, and I will initialize them. I initialize them with random values, okay, whatever they are. I initialize this with 0.35, and I initialize this with minus 0.5, for example, but you can write your own random numbers there. I have the optimizer. In the optimizer, I have now two parameters, w and b, which I want to optimize, so that's okay. And now comes my computational model. I just make 100 steps now, okay? Delete all the gradients, okay? What is my computational model now? My model is that I have w times x, right? This is the train x. Okay, let's call this just x and y. Okay, and then this way I will not overwrite them. Maybe that's better. So it's w times x plus b. Okay, this is what my models gives back. Okay, what is my error now? My error is the difference between the actual y and my calculated y, which I call now model, okay, the output of the model. The only difference is that the error has to be a number, a single number, when it could be like propagated back. This is a vector. I calculate now this for every input element simultaneously. So to have a single number for that, I will calculate the mean of this vector, okay? And this is my error. And we're done. That's it. Now I can just print out the error and calculate it. And as we show this, the error should decrease, okay? So this is the whole computation part. With this, we can do all the steps there. And you can see that we are, as we are just running this, the error will be smaller and smaller and smaller. And here, the error might not go down to 0 because there is a distance there between all the points. And I don't know what a good solution is, but we can check it easily. Let's just write a simple script which can calculate the errors. Okay, so now I will go through on all the values in X. So let me just go through all the elements in X. These are just going through the indices. And I will calculate my model on that one. So what I want to do is I get my parameter W. Okay, this will convert, this item will convert it to a number if it's just a single number. Then I will train xi. So this is just the ith element in my x vector. And for this, I will add b that item. Okay. So this is my line. This is where my line would be at the point of x, which I calculated. And then I will add this to the predictions. So append. Okay, it should be okay. I misspelled this one. Okay. And now I can just plot this. Okay, so the only thing that I want to plot is I want to plot two things on the same plot. One should be the train x values along the train y values with red dots, for example. Okay, and the other should be the train x values, the predictions with Hi there. Hello, everyone. Can you hear me? It seems that I lost my internet connection for a while. I don't know what you heard.
Oh, all good now.
All good now. Okay. So I don't know what you have seen or haven't seen. And I don't know when the connection went away. I just showed this regression problem and the plot. Have you seen this, or could you follow that one, or is it okay?
You can show it one more time.
Okay, so yeah, so okay, so what we did is we calculated the regression of a line for these vectors. I hope this was okay. And we used exactly the same model for that one. So we had a W parameter, a bias. This is describing our line. We calculated what would these two parameters, like fitting a line on X, would give to Y. And we decreased the difference between the actual Y and the Y hat that we received here. And everything was the same optimization, but we had an optimizer, zeroed out the gradients, did the computation, calculated the error, and propagated the error back. So that was all what we had. And once we had this, the error decreased. But here, we don't know whether we can reach a zero solution or not, because there's some noise in the points. But we can just plot the line. And I just did the plot of this line that we have a list of predictions. I went through the data, put all the elements into that one. And then after that, I just try to plot all the elements. So sorry, I just couldn't do this. I just want to overwrite everything. Now I can save it. So you should also have access to this code, and you can see that the blue line is actually this one. Which is fairly close to the original data points. So it's something which can be considered fairly good So we can also solve regression with this gradient-based optimization. And it's a really strong tool because for linear regression, there is a formula. If you want to fit a line on your data, that's really easy. But what happens if you want to fit something which is like sinusoidal or other things? I don't have a formula for that. But here, I could just write torch sinus x, or any model that you want, what you want to fit on the data could be done. So this is a really generic tool. And of course, it's a numerical solver, so there might be some problems for that and otherwise, but it's still really strong and a really complex model. And the optimization is like this. We have our data points, we have x points, which are the inputs, y points, which are the expected outputs, okay? And we have a computational model, we calculate it, we get some actual outputs which are compared to the expected outputs or the ground truths with according to some distance function. Here it's just an absolute value function. And then we propagate the error back and make a step, and everything is solved. So I hope this is clear and understandable, because if this is okay, then I hope you feel that gradient-based optimization is really, really awesome and really, really versatile. And if this is okay, then we would write our neural network now together. So our task would be that we will get a data set. This is called the MNIST data set. Probably many of you are familiar with this one. It contains handwritten digits, and we will write a neural network which should be capable with some like around or above around 90% accuracy to recognize handwritten digits. Okay, so this is what we will do now together. So I go back to the code, and we will start to write this, and then we can implement this element. First, we need a data set for that one, and for that I will just have some other imports. I don't know what I will use from this one. I try to tell you. So I will use NumPy. NumPy is a yeah, and sorry. So this would be the last part, and also we had shorter breaks. So is it okay if we don't have any breaks now, but we will just finish earlier around, like, I don't know, at like 7:30 in like Central European time, or around that?
Yeah, sure.
Okay, then I'll just go ahead and then okay. So we have some imports there, and then the other which I want to use maybe is that it's from Torch functional. It contains also just many functions, not at classes. This is a minor detail. It might not be important at like this level. And then I need a data set. Sorry, why is it bigger? False. It was just an auto correct there. So I have Torch Vision. From Torch Vision, I can import data sets and MNIST. Sorry, it's from this. I want to import the MNIST data set. Okay. And the other thing I want to import is some transforms. In these data sets, and like this is just to have the data set. We can look like slightly into the data set. This is just a transformation that turns our data directly to tensors, and we can use them as tensors. This is a numerical library. I might even not even need that. And this is just a functional part of Torch. It contains some other nice functions. So these are just some imports. Okay, and now try to just check the data first. Okay, so I create a data set. So let's say we have a train set, and this will be your MNIST data set, and it will be automatically downloaded. Okay, so we just have to give a folder where it will be downloaded. Don't worry, it will not be downloaded onto your machines. We run everything at, like, if you run Colab, we run everything in Google servers, so it will be downloaded to here. There are the files which are like downloaded, so you don't have to worry about this, and it's a really small data set. we can say that this is the train part. So there's a train flag in the data set. We can say that we allow to download if it's not there. And there's also a transform part where I can define a transformation. And here I will define the transformation. I will just define it right now, where my transform is this 2 tensor function. Okay. So automatically on the data set, on every point that I will use, it will be downloaded. I use the train set, and everything will be turned into a tensor. Okay. And sorry, this is a function like this. Hopefully this is okay. And if I didn't make any typos or anything, it should download the data set. Yeah, it downloaded it, and we have it. That's good. Extracts it, and we have our data available. That's good. Similarly to our training data set, we have our test set, because it's not fair, to train our neural network or something, because on that, if the neural network is fairly large and great, it should perform well. But we have an independent test set in this one, where we set this to train is false, where a new data set with images which has never seen before during the training set, will be downloaded, and it's fair to test on those. So we can use that. And we create some data loaders for that as well. And for the data loader, sorry, I didn't use my input or import. Let me just, this is torch utils data import data loader. With this, it will be fairly easy to just load the data directly to the neural network. We have a train loader which will work on the training data set. That's good. And we can have a test loader which learn on the test set. Okay. And there are other parameters for this as well. One parameter is something, for example, where we can say that shuffle equals true. It means that the data set will come in random order. So not in the fixed order, because then we could optimize for that and there might be problems. During training, we see that like the samples in random order. In the test set, it's okay to have that in just a original order, because the test set we will not train on that one. And there's one parameter here, because in the training I showed you, if you saw a cat, we can train on the cat and have good results. Then we show a dog image, then we have bad results, and we don't want to go like one after another, cats and dogs. Typically in training, we show multiple elements for the network, and this is called a batch. So we can have a batch size, which will tell us like how many images are shown. And with the data loader, it will give us this many inputs at like each iteration. So I can just define a batch size, and I can say that batch size is 128, for example, and 128. So this means that if I get a sample from the data loader, it will give me 128 random samples from the train set, but in such random that it will use all the elements, and it has 60,000 elements altogether. And for the test set, it contains 10,000 elements. And if I use this, then it will give me back the elements in order and in like 128 elements, like one by one. Okay, so this is my data set. Yeah, sorry, I have to run this because I imported the data loader late, and yeah, I misspelled torch there. Torch utils data import data loader. Sorry, it's with a capital L. Yeah, that's the problem. Okay. And that's also a capital L here. Okay, now we run it, and that's perfect. We have it, and it works. Okay. Now, the next part would be that we want to define the neural network. Okay. How will our neural network look like? Okay. So in the data, in the MNIST data set, we have images of handwritten digits. They are in 10 different classes, from 0 to 9. Okay, so 10 classes. And the task would be to classify these digits. So if a digit comes in, we can define an output class for that one. And we want to write a neural network for this one. What would be your network architecture? The input size is 28 times 28. Okay, this is an image. So altogether, if we think about this, it means that every image can be represented by a 784. This is 28 by 28 elements. Okay, so this is a vector. If just row-wise I put the elements one after another, I get a 782 long vector. This is an image for us. Okay, so this is how it will be represented. Then this is our input layer for the neural network. The first layer will contain 784 elements. That's good. I can even define this as a parameter that I can say that my input size is this 784. Okay. Then I have some layers, and at the end of the network, I want to have 10 neurons. 10 neurons because each neuron will represent a class. I have 10 classes from 0 to 9. So at the end, I have 10 output neurons. That's the output size. And in between, I can have a given number of neurons, right? Because if I, just want to show some icon of that one. Yeah, if you think about this, like, so this layer contains 784 neurons because that's our input is given. The output is also given, that's 10 neurons, but in the middle, I can put as many neurons as I want, and that's my decision, okay? So I will just put 2 layers of 500 neurons there. It could be different, but I will say that I have hidden layer size, for example, or something like it's too long. Let's just say hidden size. It's 500. Okay, that's my other parameter. Okay, so if this is done, then we can define our neural network. So first, I have 784 long vectors, then 500 long vectors, then 500 long vectors, then 10 vectors. Okay, so I will create a new class, and with this new class, it could be just inherited from an existing thing, which is a torch neural network module. Okay, and with this, everything which is defined for this torch neural network module will also define for this one. And this is also automatic differentiation. Okay, so there are 2 things which I have to define now. One is an init function. So when I create this, what sort of things should be created? And another is a forward function. A forward function would mean in computation, in torch, so forward is the computation and backward is the differentiation of this computation. Okay, so here I can define what my network does and what do I need when I initialize it. This would be the parameters. Here I define the parameters. Here I define the computation, and the backward pass will be automatically calculated. Okay, so for the forward pass, that's also an element of this, and I have an input x. And what do I do with x? Okay, so what do I need for the initialization? This is a technical thing. I don't know whether it's needed to go into this one. I will call the constructor of the superclass of this class because this is inherited. So what I need to do now is that I will just call networks self. So if in torch NL module anything is defined at creation, that should be called here. Okay, this is what I did there. It's a technical thing. Theoretically, it's not that important. So that's there. And now I have to create my parameters. What are my parameters if you think about that? So I have first a 784 long vector, and I want to multiply it with a matrix. So I multiply this with a matrix, and the matrix should be 784 times 500 long, right? So I need to create a parameter for that because every neuron was like W times X plus B, and that went through nonlinearity, right? That was the formula in the presentation which I showed you earlier. So let's define this parameter. I define W1. This will be a torch, neural network parameter. Okay, and here I said that I want to initialize this with a random tensor. Luckily, torch can create random tensors here. I will say that this is a random tensor, And the only thing I have to define here is the size of this tensor. What is the size? It's input size, and these are like the number of rows, okay? And the number of columns is hidden size, right? So this is W. Now I can do this multiplication with W1. The 1 is there because this is the first layer. And then I have the bias, okay? Once this multiplication is done, my vector representation is decreased from 784 to 500. So now I want to create a bias. This will be B1, where the length of this is just hidden size. Okay, so hopefully this is okay. This is the first layer. These are the parameters in the first layer. What would be the parameters in the second layer? In the second layer, the input is hidden size. I told you that I want a network which has like this layer structure, that 184, 500, 500, and 10, right? So now I go to 500 to 500. So this is hidden size, and that representation is also hidden size. That's good. Okay. And now I go from 500 to 10. Okay. So from hidden size to output size, and that's also output size. Okay. So now I defined all the parameters in the network. Okay. All the parameters are defined now. Now I just need to define what my neural network does. I told you that so X comes in, and I create a new representation from X. What would be this new representation? I do a matrix multiplication. It's called like torch matmul. That's a matrix multiplication between X and the W1 parameter. Okay. I do this multiplication. Great. Then for this, I will add this B1 parameter. This is my bias. This is the threshold. And then this should go through a nonlinearity. I have nonlinearity. That's why I use this functional implementation. I told you that ReLU is the most commonly used nonlinearity. This is a layer. Okay, this is the first layer of my neural network. Nonlinearity, matrix multiplication, and things like that. So that's good. What about the second layer? Now I have a 500 input representation. The next is just the same. I just change the parameters here. Okay, that's it. That's the same matrix vector multiplication. Okay, but about the third layer, I just change the parameters again. And there's one other change here which I didn't mention. At the end, larger activations means more probability. Lower activations means less probability. Here, I don't need to cut off the zero values, right? Why would I need that? Here, I don't need a nonlinearity on the output layer. Typically, people don't apply that, because with that, I will just decrease the representation. The network is sure that this doesn't belong to a class. Okay. And I return as something. I didn't speak about this earlier, but I use something which is a normalization. It's called the log softmax normalization. From every values, this will create probabilities. Okay, that's a mathematical thing there. Since this is an introductory course, I will not go into that detail. And this is my neural network. Okay, we have defined our first fully connected neural network from scratch, from matrix vector multiplications, and it's all ready and all done here. So now the only thing that we have to do is to train this network. So let's try. Hopefully I didn't make any typos with the definition, but this is not yet called, so that's good. Now we just have to write the following thing to train this one. There are a few things in network training which can be used. And one thing is that you can define the execution environment for this one. If you go there, like change execution environment for you, that should look something like that. You can train something on a CPU, or you can train something on a GPU. If you change it there, you can switch to a GPU and training will be faster. No, I will not do that. This is a fairly simple model. We can train it on the CPU. But if you want to do that, you can check devices. Like Torch also supports not just automatic differentiation, not just tensor operations, which are two really cool things, but it also supports calculation on GPU. You can do something to check, like whether CUDA, which is a operations for GPU, and you can check whether like CUDA is available. For me, CUDA will not be available, but if you change this in the environment and rerun everything, CUDA will be available for you. And so, for example, you can create a script where if CUDA is available, you can do a calculation on a GPU. If not, you can create everything on a CPU. So I can say something that I want to create a device where this is a GPU, if CUDA is available, if Torch is available, okay? Otherwise, if it's not available, like for me in the current state, then this is CPU, okay? And if I do it like this, then if a GPU is on the system, the code will be automatically executed on the GPU if you put it on this device, okay? So that's good. Now, let's create our neural network. I create my network. That's the name of that. This is our model, okay? And I can just say something to device, okay? Normally, it's created on the CPU. So for me, this doesn't do anything. But if I change the environment to GPU, then it maps it to the GPU automatically. And you don't have to know anything about CUDA. You don't have to know how to program a GPU. It automatically goes there. Okay. Now, we need the next thing. We will create an optimizer. So we can just get this out from similarly as we used it earlier. So our optimizer, if you remember correctly, it was in the torch.optim package. And I can just use again the same old Adam optimizer that we used earlier. So torch.optim Adam, okay. And here we had two things. We had a learning rate, that's a parameter. I will just, sorry, I plan to write a bit longer script, so I put the parameters here. So this is 0.05, okay, that's our learning rate, a fairly low one. And we have to give here the parameters, okay. I could get all these parameters as a list, but I have something even cooler since we inherited this from Torch and a module, and every module has a collection of all the parameters. I can just write this. This is the parameters of my model, okay? And it will contain all the parameters which are there, okay? So now I have my optimizer. I can just do training, okay? So what we can do is that now, let me just do another import because it would be nice. Sorry, I forgot to import this one. There is a tool called TQDM. It has nothing to do with machine learning. It just contains some nice and fancy progress bars. So I will just rerun this cell. It will have some progress bars to show where we are on the data and where we are in training. Okay, so I just imported this TQDM also up there at like the definition. And now we can go through our training data. So now I can just say that I can get a batch from the training data. For this, we created data loaders, right? So I can use this TQDM, and I can say that this goes through the train loader. This will automatically go to the train loader, okay? And I can even create a description from that. So I can say the description, like every step, write out something like that. Epoch and okay, yeah, I didn't speak about epochs. Sorry, I will go back now. Let's just skip this part and I will come back here. Okay, at the end, please make me remember to come back here and we will do this. So I just go through the data, okay, and in the data, every batch has two things. The first element will be my input, and the next element will be my expected output. Okay. So I have these two elements. If this is okay, I can also put them on a GPU if I would use a GPU, because these are on a CPU normally. So I can just say X to device and Y to device. Okay, I mapped up. This is nothing, just a technical thing to map them. Okay. So my problem is now that I said my input is a 784 long vector, but unfortunately this is not true. If I would check X now, it would be a 28 times 28 image. So I have to reshape them. For that, I will just say that reshape, sorry, torch reshape x, okay, and I can define the dimensions of x, which is 784, and I have this -1 as well. -1 is something that if I have matrices, it will be one for one dimension, it will be automatically given. So how many is left there? And since I use batches of arbitrary numbers, at the beginning I defined it as like 128, but it could be anything. This would be now 128, but if I change the number there, then it will be something different. Okay, so now I have my input. Now we are really close. It can just go through my model. I will do my calculation, get my neural network, and then with this I get y prime. Yes, so this is the output from the model, and this now comes my error. Okay, what would be my error? For my error, I want to calculate something which is called cross entropy loss. Okay, and I create here as a separated function. I mentioned this in the presentation. This is a logarithmic distance function, typically to compare two distributions. So the distributions of the output classes and the original ones. And in the torch neural network module, this is also available. So I will just use cross entropy loss as my criterion here. Okay, so what will I compare in this one? I will have two things. I will have y prime and y. Okay, so this is my error. Okay, if error is done, that's great. Then what else can I do? I will delete the gradients. So here I would that optimizer 0 grad. Okay, if the gradients are deleted, now I can propagate the error back. Error dot backward. Okay, and I can just do optimizer dot step. Okay, and so this, as it is, this part is not really finished, but this would go through the data and optimize everything here for me. That's good. That's like really useful and great. But since the changes are really small and I have many parameters, typically it's not enough to go through the data once. We go through normally the data multiple times, and this is called epochs. So one epoch is something where we go through the data once. We have seen all the samples. Here we have 60,000 samples. So once we've seen every 60,000 samples, that was one epoch. So that means that once we went through the data, but typically for training, we need more. So I will use like 5 number of epochs now, which means that here I can just write down like which epoch is in training. Okay, and I need an epoch for that. So an epoch would mean that I put this into another other for loop, and I can just create a range here which goes through the number of epochs. Okay, and then there's a description for this. This is for TQDM, because then I can have like fancy descriptions. Okay, training. Okay, and then it should just describe this. Okay, and here now I can write that. Okay, move everything like inside the bit. Okay, and I can write that epoch something +1 is in training. Okay, so that should do the trick. And if I do this, then training starts. And let's my network is not defined. Here I wrote network, sorry, instead of my network. That's a typo. Let me just correct my box quickly. T range. Didn't I? Oh, sorry, this should be equal. Okay. Okay, so now training goes, and you can see that there is this nice progress bar, how we go through the different iterations and things like that. So now the code is okay, and it doesn't contain any typos. If you want, if you check the Colab notebook, then you would be able to see that, hopefully. and then you can try to implement it or correct your implementation. So training goes now, and we can even check there are two things which we don't see. I want to see two things, two additional things in that, and because of this I will stop the training now. One would be good to see how the error is decreasing. So at every end of every iteration, I could just write out. Okay, maybe it will run faster than before I could stop this. We could write out what's the proper error, and it would be also good once training is done to do some testing. Okay, so we should also wait for that one. I don't want to just close this, but maybe I will have no other options. But okay, we still have some time, but I want to wait because it's just a couple of iterations, but then. Okay, so now it stopped. Okay, I think it went through all the maybe four. No, it went through 3 epochs. Okay, so I want to add two things. At the end of every epoch, it would be good to write out like what's the current loss. So here I want to print something out. But for that, we want to calculate like a mean error in every epoch. Okay, so I will write here something which is the train loss. And here in training, I want to average out all the, okay, I just still want to train this, okay, or save this, sorry. Here I want to, once I have the error here, I want to add all these elements to this train loss value. Okay, so to train loss, I want to add something, and this is error. And error is something which has gradients. So now if I just want to use this as a single number, then I want to just get this as a number, okay, and then add length train loader. I have train loader here. So how many elements I have? So what I did here is to calculate the average. In the average, normally first we sum all the elements and then divide it with the length. Here I add an element divided by the length, so that's the same basically. I do a bit more divisions, but that's something that we can do here. And then I just want to write out that in epoch, in a given number, epoch plus 1. So this is where we are currently in the first epoch out of the number of epochs. How much was the loss? So let's just say that, okay, it's there, and the loss was, let's print out train loss. Okay, up to maybe 2 floating points numbers. Okay, so this would just at the end of an epoch print out what is the train loss or what is the error on that. That's a number. If training is correct, it should be decreasing. That's good. But it doesn't really tell us how good is the performance of the network. The performance could be measured on an independent test set. So that's what that should be implemented here. We also created an independent test loader. So for that, I just want to like copy this part and create a test part from this one, where we can go through all the test element and calculate how many good elements we had that and how many bad decisions were made. First, I do something which there are two tricks which can be done. One is that we can write a block which is torch no grad. It means that here you should calculate no gradients. It's not needed because here we will not train the network. We will not change the weights. Another way to do this, that for every network, you can put it in all network into train mode, or you can put all networks into eval mode. That's the same part, but now I just do it like this, okay? And what I want to do here is, I want to calculate again the loss. So I had this train loss. I want to have something similar, which would be my test loss here. What is my loss? And also, let's calculate how many correct samples are and how many samples are all together. Luckily, we know that in this one there are 10,000 samples, but let's just count it. Okay, so I have two numbers, correct and total, as 0 and 0. and then I will get batches. Now I will not get it from the train loader because we hope we optimized on that fairly well. We have it from the test loader, and let's just write out testing or something simpler. Okay, so what about the calculation? We get the data, put it on the GPU, reshape it, go through the model. That's good. I don't need this zero grad because we will not have gradients. That's good. Okay, so model is calculated. I have my loss function. That's good as well. For the loss, I can again summarize the loss, but now I want to add this to the test loss. Okay, error.item, and this is the length of the test loader. This will calculate for me the average loss, which is okay, and I can print this out. At the end, I can just write something, print test loss, for example, test loss, and then this should be test loss up to 2 digits, floating point. Okay, the optimizer is not needed, the backward is not needed, and the other parts which I wanted to calculate how many correct answers do I have, and what was the number of total samples. The number of total samples is fairly easy because what I can just do is I can just calculate how many elements I have in X. Okay, so for total, I have batches. In every batch now I have 128 elements, but it could be arbitrary, and I want to have a fairly generic code. I can just add how many elements were there. Correct is a bit more difficult to calculate it, because when will I say that something is correct? Something is correct because y prime is a vector, and the largest element of y prime will give me back what was the class. The classes are from 0, they are going from 0 to 9. So 9 represents digit 9, 0 represents digit 0, and things like that. And so in y prime, I have to find what is the largest activation. I can do that with argmax, which is the argument to max in y prime, okay? And so this means like which index is the largest in y prime, and I have to do it along the first dimension. That's the last dimension. Y prime is a matrix of 128 by 10 elements. Okay, the 10 elements belong to class, and this is the dimension I want to find the largest activations. And now I can check where these values are equal to y. Okay, if these are equal to y, that's good. These are the number of correct elements, and I can just sum them together. Okay, and if they are summed, then I can say that generate an item for that and add this to the number of correct elements. So that's good. And if this is done, then here I can also I can also print out the accuracy of the current method. So I can just print out something that test accuracy, and test accuracy would be the ratio of the correct elements and the total number of elements. So correct divided by total elements. And if I want a percentage from this, then I can multiply this by 100 and print this out to up to 2 floating point numbers. Okay, and percentage. Okay, so this is done. Hopefully the code is okay. Let me just check whether I made some typos or not. Oh, yeah, I'm a bit risky in this one because now training will be executed for 5 epochs. Sorry, are there any questions? Please let me know if there are any questions. Okay, if not, then let's just hope it will run. I should have just run this for a single epoch to maybe check this one, and then we could see whether this is working correctly or not. But yeah, I didn't do that, so now we have to wait. Now we are at the 3rd epoch, but at least what is working and correct is that we can check the loss function. So loss is 150 now, these are just numbers, so you can just do this for comparison. We started with a significantly larger number. It was like 6,000. So it is decreasing, which seems to be okay. But really, the loss is just not that meaningful. The accuracy would be something that just which could be meaningful for us, and that could signify how good our method is. There's this epoch and one more, and after that we will see whether I made any typos or not. I'm a bit afraid maybe I made a typo and then the testing will stop there, but we will see soon. If I made them, I will just run this for a single epoch and then we can check this. Soon we will realize this. Okay. No, okay, so that's great. I didn't make any typos in the test part. So what you can see here is that we ran for 5 epochs. From the original 6,000, the error went down to 28. On the test set, our epoch is 20, which is even less. That might be just luck. But altogether, what is more important, that we created a neural network which can like recognize handwritten digits with 90% accuracy. Okay, and this 90% accuracy is great, but which is even more important that if you check this part and go back to the beginning, how we solved the equation, it's exactly the same. The only thing that changed is the data, that we load different data and a different neural network. If you want to train your own deep neural network now, you have to change like this model, like this one slightly, and the data, how the data is coming in. And if you do these changes, then everything will be great, and everything can be just done simply. And let me just show you another thing that also we did this from scratch, where we did all these multiplications and everything like that. It's even simpler in PyTorch, but I hope with this you understand that what this multiplication is. You can create like direct layers in PyTorch. You can say that I create layer 1, which is NN. It contains something called a linear layer, which we did, and you could just write this instead of those 2 lines. You could just write input size and hidden size. Okay, and instead of the matrix vector multiplication, you can just directly torch, and you can just define it like this as well. Okay, so this is just an extension that instead of like these 2 lines, you could write something like that. And that's the same for that one. And that one, so just in 3 lines of code, you could define the neural network. You do the calculation as well. Instead of that, you can just write L1, and then a neural network turns out to be really simple. But I hope that this helps you to see what's happening inside the neural network. And it's nothing else than just matrix vector multiplications with given parameters. And these parameters are optimized with a gradient-based method. And with this, we trained our first neural network from scratch, and we managed to reach like 90% accuracy with the task where you want to optimize for digits. And this is like the basic building blocks for supervised training, because this was a typical supervised training scenario on X and Y set of data, and we optimized a deep neural network with gradient-based methods, which is like the current new sliced bread of optimization, and most of the problems are solved by this. So this is all that I wanted to show you. The code is still and will be available. Also, if you have any questions, then just please ask it now. I'm here. You can write it to me. You can ask it in the chat, or now I'll come back and I will see you, and I can also see you if someone raises his or her hand. And also later on, if you have any questions, you can write me an email, and you can find me. It's I don't know whether it's, this is my email address. So if you have any questions, concerns, anything, like, you can you would be able to reach me via that email. So that was all that I wanted to tell you. Really, thanks for your attention. Please, I'll be here for a couple of minutes, and let me know if you have any questions.
Hi, Professor.
Yes, please.
Yeah, I copied your code from the notebook, from the collab, and I'm trying to run it myself. However, I get an error regarding the y prime equals model x line. It says that they expect one positional argument, but two were given. Do you maybe know why this happens? This one, yeah.
Here with this one?
Yeah.
But from this model X, I don't know, but I don't know whether you can share your code with me or share your desktop or something. I think it might be something at the forward. My guess would be that this X is missing in the definition of the network, but without seeing the code is just a guess. But I don't know whether you have options to share it or not. But if you share, we can find the error together.
Yeah.
Okay.
Yeah,
so
it's this one.
Yeah. Can you go up where the network is defined? There's something class. Yeah, class in it. This is yes. No, X is definitely there. It's not what I was thinking. I don't know. Can you go back down? Then sorry, where the error was.
Yeah.
Oh yes. So I'm just trying to. Yes. No. Why? Oh, it's in the ReLU. Okay, no. Go back to the. Okay, sorry. Go back to the network definition, please.
Okay.
The problem is there. So here, yeah. So the whole thing should be in brackets. There should be another bracket where you are. You should open another bracket.
Okay.
And close it at the end of this one. No,
Okay.
not there. At the end of the line. Sorry.
Yeah, like this.
Yes, and also in the and also in the first two. Okay. No, that was okay. That was okay. Please, that's okay because there's no ReLU in that one. Okay, and now in the first line between the two brackets.
Here.
There, yeah, you should write torch point matmul, matrix multiplication. I sent it to the chat, but matmul, yeah. Okay, and similarly the second line. Okay, now try to execute this code, yeah, and so then the one below and hope that it will work. Okay, yes, so now we get a different error. So this is okay, this is solved, but let's check then.
Yeah, Professor, I don't want to take any more of your time, so I can just copy it from what you did. So I was wondering.
That's okay. Okay, it's up to you. But if you would have any problems at any point, then just let me know, and I can we can come back there and check it.
Yeah. Yes, thank you. I don't want to waste any more of your time. I'll just do it. Yeah, thanks.
Oh, please. Okay, thanks. Thank you. Okay, so let me know if you have any questions or any problems. If it's clear and understandable, then really thank you for the participation. Thank you for being here. That was like all which I planned today, and I hope you see something how neural networks can be created and how they are trained, and then you will continue with other methods from supervised and also unsupervised training. So please have a nice day, and thanks for being here.
Thank you. Bye bye.
Bye everyone. Goodbye. Thanks.